Hello there, and a very warm welcome to Sleepy Scientist's Official. I'm genuinely chuffed you've chosen to spend a moment here with me. No matter how your day's unfolded, or what little thoughts are still doing laps about your mind, you can simply set them down now. There's nothing pressing you need to do, nothing important you need to cling on to. Just make yourself comfortable. Let your breathing settle into something gentle and steady, easy and natural. And when you're ready, let your imagination drift outwards, past the edges of this little world, past the noise and the bustle, into that enormous, glittering, ever so quiet city of stars we all call home. It's vast, it's calm, and it's waiting to carry you into rest. Tonight, we're not simply gazing up at the stars from afar. We're going to slip quietly in amongst them. We'll drift along like a tiny, aware speck of dust carried on a slow breeze through the most magnificent structure we'll ever truly know, the Milky Way galaxy itself. Think of this less as a list of facts and more as a tale, one softly etched in gravity and starlight, unfolding over billions of years, a tale of things being born, things falling away, and everything changing ever so slowly with remarkable patience. And somewhere within that story, we exist too. Small, yes, but beautifully, inseparably part of it all. So, make yourself cozy. Shift into a position that feels kind to your body. Let your eyes close if you fancy it. And when you're ready, we'll start our gentle little voyage from the very outer edges of our galactic home, spiraling ever so calmly inwards, towards the quiet mystery at the heart of this enormous cosmic whirlpool we call our own. No rush, just a slow, peaceful drift through the stars. Our little journey starts somewhere rather unusual, not in the blaze of light, but in the quiet shade just beyond it. Not amongst the stars at first, but in a kind of gentle darkness, something you can't quite see, yet can feel, like a soft but powerful force tugging at everything around it. We begin out in the galaxy's halo, the very outer layer of the Milky Way, a huge, almost empty sphere that wraps itself around the entire night sky you know so well. If you imagine our galaxy as a city, full of glowing street lamps and brilliant windows, then the bright, star-filled disk would be its lively, sparkling center, all warmth and movement and soft radiance. But the halo, well, that would be the vast countryside beyond the city limits. Dark, peaceful, mostly untouched, stretching out for thousands of miles in every direction. It doesn't shout for attention like the lights below, but it holds everything together in its own quiet way, with a patient, invisible weight that keeps the whole beautiful structure from falling apart. A calm, steady embrace around the galaxy's glowing heart, quietly doing its job, just like a lullaby, humming beneath the melody. This halo, as it turns out, is home to one of the universe's most fascinating puzzles, dark matter. And we begin here quite deliberately, because although we can't see it, it's really the quiet genius holding our galaxy in place, the true designer in the background. Thanks to careful research by astronomers and brilliant data gathered by organizations such as NASA and the European Space Agency, we've learned something rather astonishing. Everything we can actually see, the stars, the swirling gas, the delicate dust, the planets, all the little bits that catch or create light, makes up only about 15% of the galaxy's entire mass, which means the other 85%, the vast, overwhelming rest of it, is this gentle, mysterious thing we call dark matter. It doesn't glow, it doesn't shimmer, It doesn't twinkle back at us. It doesn't mingle with light at all. Not one photon reflected, absorbed, or sent our way. Completely invisible to every telescope, no matter how clever or advanced. So if we can't see it, how are we so sure it's there? Well, that's part of the magic of it, really. We can feel its presence through the way it choreographs the stars, guiding their movements with a calm, unseen hand. It's not loud or bright or showy, but it leaves little fingerprints in the dance of the cosmos itself. And that's how we know it hasn't drifted away into myth. The clue to the whole thing was hidden in the way stars move, or more specifically, how quickly they whirl around their galaxy's center. Back in the 1970s, Vera Rubin, a wonderfully sharp astronomer working at the Carnegie Institution in Washington, was looking at how the Andromeda galaxy rotated. She assumed, quite sensibly, that the stars far out on the edges would drift along at a more leisurely pace, a bit like how Pluto ambles gently around the Sun, while Mercury zips round with far more urgency. That's exactly what Newtonian and Keplerian physics would predict, after all. But nature, as it loves to do, had a surprise in store. The outer stars weren't slower at all. They were moving just as briskly as the ones much closer in, almost as if the entire galaxy were spinning together, evenly and smoothly, like a great old vinyl record turning on a player. Of course, that simply shouldn't have been possible, unless something else was there. Something silent, invisible, unimaginably heavy, stretching out through the galaxy's halo, holding everything in place with a firm but unseen gravitational embrace. Without that extra mass providing its subtle glue, those fast-moving outer stars would have been tossed clean off, flung into the empty dark between galaxies. But they weren't. They stayed exactly where they were meant to be, dancing along at full speed, as though guided by a hidden hand. Vera's discovery, repeated and confirmed time and again, even in our own Milky Way, became the very first solid piece of evidence that dark matter wasn't just a clever idea, but a real and essential part of our cosmic home, quietly at work, shaping the heavens while we sleep beneath them. The true nature of this substance is still one of the loveliest mysteries in all of modern physics, the sort that keeps clever minds gently buzzing with curiosity. Some physicists, including those working at CERN, wonder if it might be an ocean of exotic, as yet undiscovered particles, things with names like WIMPs, or weakly interacting massive particles, quietly swirling just out of sight. Others think perhaps the answer lies not in particles at all, but in a soft rethink of gravity itself. Ideas like MOND, or modified Newtonian dynamics, which suggest the universe might play by slightly different rules than we once assumed. It's a friendly, ongoing conversation in the world of science, one that unfolds in journals such as Nature and Science, where the debate carries on warmly and energetically, like scholars chatting over tea. And though the answers are still hiding in the dark, one thing's become beautifully clear. Without this gentle, invisible framework holding everything together, the Milky Way wouldn't be here for us to marvel at today. It never would have gathered itself in the early universe, and it certainly wouldn't have held on through the ages. Long, long ago, it would have quietly unraveled, its stars wandering off into the great vast beyond. So as we imagine ourselves drifting in the calm dark of the halo, we're not in emptiness at all. We're floating in a sea of the unknown, a soft gravitational essence almost like a cosmic mist that holds our whole corner of existence in a peaceful, patient embrace. It's the silent architecture beneath the stars, the unseen foundation that lets the galaxy shine so brightly above us. Not noisy, not rushed, just present, dependable, and quite extraordinary. And still, even out here in the deep, gentle dark of the halo, there are tiny hints of light to be found if you know where to look. Scattered through all that quiet space are some of the very oldest stars the universe has ever made. The great-grandparents of the galaxy, if you like. Astronomers call them population 2 stars. They don't blaze like younger suns do. They just glow softly, often with a warm, reddish twinkle that feels rather comforting, really. Ancient little lanterns, burning steadily through time. You might hear scientists describe these stars as metal poor, which sounds a bit odd at first. But in astronomy, metals simply means any element heavier than hydrogen and helium. Things like carbon, oxygen, iron, or silicon. The building blocks that eventually formed planets, oceans, even us. These very old halo stars were born long before the universe had time to brew much of that heavier stuff. So they carry only the tiniest trace amounts, sometimes less than 100,000th of the metal content found in our own sun. Imagine that. Stars formed when the universe was still fresh and wonderfully simple, holding barely a whisper of the elements we see everywhere today. Quiet, delicate, old, and gently reminding us just how long this cosmic story has been going on around us. Why does any of this matter, you might wonder? Well, because these little details are how we learn a star's life story. These ancient stars are gentle survivors from the universe's earliest days, the cosmic dawn, the very start of it all. They formed within the first billion years after the Big Bang, born from beautifully simple clouds of hydrogen and helium, untouched, unseasoned, just as the young universe first made them. Back then, there hadn't been generations of stars yet, living bold lives and ending in dramatic supernovae, the enormous stellar explosions that eventually forged and scattered heavier elements like iron, oxygen, and silicon far and wide across space. Which means, when you glimpse the soft light of one of these very old stars, you're seeing a piece of a time before planets like Earth could even dream of forming. There was no iron yet to shape a planet's core, no silicon for solid ground, no oxygen for water to ripple and shimmer with life. In a way, they're like fossils, not buried in stone, but shining in light. Their simple composition speaks of a universe that was younger, stormier, fiercer, and wildly energetic, yet still laying down the first gentle chapters of existence. A quiet little star, whispering tales of a turbulent youth, all in the color of its glow, holding the history of the cosmos in its very makeup. There are a few of these stars that have lived for such an unfathomably long time. They almost feel like characters from an ancient myth. Take, for instance, the faint little red dwarf drifting quietly in the halo, the one astronomers call HD 140283, though most of us know it better by its rather poetic nickname, the Methuselah star. It's been studied quite carefully over the years, and the results were, frankly, gobsmacking. Early readings from the Hubble Space Telescope hinted that this star might be 14.5 billion years old, which raised a few eyebrows, because the universe itself is only 13.8 billion. Quite the cosmic contradiction, really. But as science enjoys doing, the answer softened with time. With better models and sharper data, astronomers, including those working with the European Space Agency, refined the estimate to a still remarkable 13.7 billion years, which means this tiny sun flickered into being when the universe was just a wide-eyed baby, only about 100 million years old. Long before the Milky Way galaxy had formed itself into the calm, swirling spiral we see today. In fact, HD 140283 didn't begin its life here at all. It's a bit of a traveler, a cosmic newcomer, born elsewhere in the vast dark, long before our galaxy assembled itself into shape. By the time the Milky Way took form, this star was already shining quietly in the wider universe, ready to drift in and make itself at home in the halo. A star with a long journey behind it, older than the galaxy we call ours, carrying a bit of distant starlight story along with it as it wanders through the quiet dark. Rather lovely to think about, really. Celestial history gently twinkling above, while the rest of the universe hums softly on. This brings us to one of the most remarkable ideas astronomy has gifted us in recent decades, something almost poetic in its surprise. The Milky Way, you see, isn't a quiet, untouched little island floating alone in space. It's had quite the appetite over the years. Scientists sometimes describe it, rather colorfully, as a bit of a cosmic cannibal. Over roughly 12 billion years, it's grown by drawing in, merging with, and absorbing countless smaller galaxies, one gentle cosmic meeting after another. Now, the stars living in the galactic disk, the glittering spiral we're all familiar with, tend to orbit in a fairly neat, predictable sort of way, sweeping around the center in a flat, orderly plane. But the older stars out in the halo, their movements are wonderfully untamed. They circle the galactic center at steep angles from every direction imaginable. Some even travel the opposite way around, a retrograde orbit, if you like, moving backwards against the galaxy's general spin. Imagine a bustling train station late at night, with travelers arriving softly from north, south, east, and west, each following their own path, each carrying the quiet echo of where they've come from. That's rather what the halo feels like, a great cosmic crossroads, where the motion of each star gently hints at its origin story, whispered not in words, but in starlight and movement. Those ancient halo stars, drifting in all sorts of directions, are the proof that the Milky Way was built piece by piece, shaped not in isolation, but through the company of others, over an unimaginably long stretch of time. A galaxy made from meetings, journeys, and quiet beginnings, all softly spinning above us as we begin our own gentle drift into sleep. We can, these days, trace those ancient galactic mergers with an almost jaw-dropping level of detail, largely thanks to the work of the European Space Agency's Gaia Space Observatory. Gaia isn't quite the sort of telescope that captures glittery, postcard-ready pictures. It's more like an extraordinarily clever measuring device, precise to a degree that feels almost bewildering. For well over a decade now, it's been quietly and patiently charting the positions, distances, and motions of more than 2 billion stars across our galaxy. Rather like conducting the first truly thorough census the Milky Way has ever had, complete with a little map of how everything is moving too. And tucked within all that data, astronomers have spotted something rather lovely: stellar streams. Think of them as soft, river-like trails of stars, all drifting through space together, bound by a shared history. They're the subtle remains of tiny dwarf galaxies, that brushed a bit too close to the Milky Way long ago, and were ever so gently, yet irresistibly, pulled apart by gravity. Their stars, once neatly gathered in little galactic homes of their own, are now stretched out along sweeping arcs across space. Quiet, graceful trails, like the galaxy's own old scars, celestial stitch marks from past encounters. It's not a violent sort of noise-making chaos, more of a patient, cosmic unraveling, a gentle reminder that even the grandest galaxies grow through little meetings, tiny stories, and soft gravitational embraces that leave behind ribbons of starlight, celestial history, drifting like quiet misty rivers overhead, giving the Milky Way its tapestry of past lives, all written into the sky above as we wind down for rest. One of the most memorable chapters in the Milky Way's past is the rather curiously named Gaia-Enceladus merger, or as some astronomers fondly put it, the Gaia sausage, thanks to the distinctive sausage-like swirl of star orbits it left behind. About 10 billion years ago, a chunky little dwarf galaxy, maybe around a quarter of the mass of the Milky Way's disk back then, drifted in and collided with the young Milky Way. It was quite a turbulent meeting, the sort that likely warmed and puffed up the early galactic disk, nudging stars out into the halo and helping shape the very structure we call home today. And the galaxy didn't stop growing there. A more recent little encounter is still quietly unfolding above us even now. The Sagittarius dwarf spheroidal galaxy has been orbiting the Milky Way for billions of years. Each time it swings close, the Milky Way's gentle but enormous tidal forces peel away a few more of its stars, stretching them into a delicate, meandering stream that softly wraps around the entire galaxy, rather like a faint, silvery ribbon drifting round a nighttime sky. In a sense, we're watching the Milky Way slowly, patiently welcoming and absorbing a smaller neighbor, bit by bit. It's not a loud or hurried process, more of a slow, graceful gathering, one star at a time. And this, astronomers tell us, has been happening since the universe was young and will carry on for ages yet, long after we've nodded off to sleep. A galaxy shaped by quiet reunions, cosmic embraces, and starry heirlooms, all drifting gently overhead, carrying on their dance while we rest beneath them. So, as we imagine ourselves drifting gently out here in the halo, we're not floating through emptiness at all. It's more like an old resting ground, a quiet galactic graveyard, yes, but also a sort of museum, softly lit by the faint glow of impossibly ancient stars. All around us are those metal poor, lovingly old suns, the very first building blocks that helped galaxies learn how to form in the early universe, and woven in amongst them are the stretched out remnants of tiny galaxies the Milky Way encountered long, long ago. Not trophies, exactly, but quiet keepsakes of a youthful galaxy still finding its shape. It's a place of extraordinary calm now, hushed, patient, almost sacred in its stillness. But if you listen very carefully, the history is there. Not loud, not dramatic, just a deep, gentle hum. Little echoes from a time when the Milky Way was young, wild, fiercely creative, and forging itself into something vast and beautiful. A serene night sky built on old stardust and older stories, quietly holding all that history, while we ourselves soften into rest. Let's very gently now let ourselves drift a bit closer in, leaving behind the soft quiet of the outer halo and slipping into the brighter, more familiar parts of the galaxy. We're approaching the galactic disk, the true heartland of the Milky Way. It's lively in its own graceful way, like a huge, slow-turning platter of stars, dust, and swirling clouds of gas, stretching an incredible 100,000 light-years across. If the halo felt like a calm, empty countryside at night, then the disk is more like a softly glowing, wide-awake city center, a peaceful metropolis made of starlight. And just like any great city, it's full of subtle structure and character. Not noisy or chaotic, really. More of a gentle rhythm. Each region with its own little design, its own quiet neighborhoods, patterns, and ways of being. Cosmic boroughs, if you like, each stitched together into something beautifully ordered, endlessly fascinating, and wrapped in that slow, comforting spin of the galaxy itself. A city of stars, with its own calm architecture, waiting to show us a bit more of the story before we all drift off for the night. The first thing you'd likely spot, if you were floating far enough out to see it all from the outside, is that the galactic disk isn't quite the perfectly flat circle you might expect. It has a gentle little warp to it, rather like the brim of a soft felt hat that's been ever so slightly twisted out of shape. One side bends up a touch, the other dips down. Nothing dramatic, just a quiet rhythmic wave that gives it character. This subtle curve is most noticeable in the outer regions of the disk, just beyond the galaxy's main spiral arms, the quieter outskirts of the metropolitan glow. For years, astronomers weren't quite certain what caused it. Perhaps it was the faint gravitational memory of an ancient galactic encounter, or maybe the soft influence of vast intergalactic forces like magnetism stretching between galaxies. But these days, the strongest little clues point towards the Magellanic Clouds, two charming, slightly irregular dwarf galaxies that orbit near the Milky Way. As they drift along in their slow loops around us, their combined gravitational pull, along with the invisible weight of the dark matter they appear to carry in tow, gives the outer disk a gentle tug, almost like a quiet wind catching the edge of a ribbon, twisting it into a smooth, graceful arc that holds its shape through the ages. It's a rather lovely reminder, really, that nothing in our galaxy exists entirely on its own. Every star, every cloud of dust, every bend in the galactic brim is softly linked by those invisible threads of gravity, all gently pulling and balancing, like constellations connected in a slow celestial embrace. Even the warp itself is part of the lullaby of stars, a testament to the quiet wonder that everything out there, no matter how far apart, is part of the same vast and patient story. As we drift a bit nearer in, the galactic disk begins to reveal its shape in two lovely little layers, the thick disk and the thin disk. And the thin disk, rather beautifully, is where we ourselves happen to live and breathe. It's a fairly slim, gently spinning plane, only about 1,000 light-years thick, quite narrow when you think of the size of the whole galaxy. And it's here that new stars are still being born, softly gathering from glowing clouds of gas and dust, stirring ever so slowly like celestial nurseries lit by night lamps. This part of the Milky Way is home to the younger stars, rich in those heavier elements astronomers call metals. You'll find dreamy blue open clusters shimmering like little gatherings of fireflies, and vast, illuminated clouds swirling gently around them, the sort of cosmic workshops where stars learn to ignite. It's the more modern, ever-changing side of the galaxy, lively and dynamic, but not loud. There's a sense of gentle renewal here, constant but unhurried, stars forming, clusters shifting, stardust gathering itself into something new. A quiet rhythm of creation that carries on while the rest of the universe slumbers around it. The thin disk is the galaxy's softly glowing present day. Its serene and restless, but poetic frontier of becoming. And right here within it, we spin too. Part of that same slow story of starlight and dust, carried on a calm, gravitational breeze. Drifting gently just above and beneath the thin disk is its quieter neighbor, the thick disk. It's a bit more rounded and airy, less like a sleek sheet, more like a softly puffed cushion of stars and space, stretching to about 3 times the thickness of the thin disk below it. The stars here tend to be older on the whole, and carry fewer traces of those heavier elements, the metals that younger stars have gathered over time. Their paths around the galactic center are a bit more looped and elliptical, often tilted at gentle angles, hinting at a past that was rather lively and unsettled. Many astronomers think of the thick disk as a sort of remnant left over from the Milky Way's very early years, a time when the galaxy was still finding its shape and things were a bit more turbulent than they are now. Some even suspect it may have gained its cozy, puffed-up appearance through ancient encounters, perhaps nudged into its present form by mergers like Gaia-Enceladus merger. If the thin disk is the galaxy's softly glowing modern world, all shimmering starbirth and quiet motion, then the thick disk is its old quarter, a layer of beautifully aged history, resting just above those younger, gently spinning streets below. A calm, star-filled loft above the metropolis, holding memories of long, patient ages. Still, dignified, and rather lovely to think about as the universe hushes itself for the night. And it's here, nestled within that thinner, gently spinning disk, that we come to the most recognizable little flourish in our galaxy, its spiral arms. For ages, figuring out their exact pattern was almost comically tricky, a bit like trying to map the winding streets of London while sitting on a misty park bench right in the middle of Hyde Park, with the rest of the city blurred by fog and trees. We're tucked inside the very structure we're trying to describe, you see. And to make it even more of a puzzle, huge veils of interstellar dust softly drift between us and the distant stars, blocking the longer views. But astronomy has its quiet ways of working out such things. Radio astronomy, for instance, can listen for the gentle radio whispers of hydrogen gas, signals that drift straight through dust as though it weren't even there. Then there's infrared astronomy too, which notices the soft heat glow of stars shining patiently behind those dusty curtains. By listening to those subtle signals and warm glimmers, astronomers have pieced together a sort of hand-drawn map of where the arms ought to be. Not perfect, perhaps, but wonderfully good enough to guide our imagination through the city of stars. It's all been worked out layer by layer, a cosmic chart made not by looking around us sharply, but by listening gently, sensing warmth, and tracing the faintest of patterns, rather like discovering a whole universe by torchlight and intuition, soft, steady, and a little bit magical. We think of the Milky Way as a barred spiral galaxy, meaning if you were far enough away to take it all in, it wouldn't resemble a tidy little pinwheel at all, more like a vast, softly swirling stellar whirlpool, with a gentle bar of stars stretching straight across its center, like a quiet spine of starlight holding the swirl together. From the tips of that starry bar, 4 major spiral arms curve outwards in those long, graceful sweeps. Astronomers have named them quite poetically too: the Norma arm, the Scutum Centaurus arm, the Sagittarius arm, and the Perseus arm. And as for us, you, me, our little corner of existence, well, our solar system doesn't sit right in the middle of those grand arms. We're a bit more tucked away, living in a smaller, quieter stretch of stars and gas known as the Orion Spur. It's sometimes called the Orion Cygnus arm as well, a gentle little spur, nestled peacefully between the Sagittarius arm and the Perseus arm. So really, we're drifting in a quieter suburb of the galaxy's luminous city, not front and center, but perfectly placed to witness the glow of it all just the same. A rather lovely little nook in the spiral, quietly spinning through space, while the stars keep their soft, ancient vigil above. This gentle little corner of the galaxy, our quieter spur, might well be one of the key reasons we're here at all, able to wonder about stars without being rattled by them. The larger spiral arms are undeniably breathtaking, glittering, bright, spectacular, but they're also rather intense places to call home. They're packed quite densely with enormous, short-lived stars, the sort that burn brilliantly but bow out in dramatic supernovae, spilling powerful bursts of radiation across space. And where stars are crowded close together, there's always a higher chance of a bit of cosmic jostling, gravity giving the odd gentle nudge in ways that can unsettle whole planetary systems. But out here, where our Earth quietly spins, things are calmer. Our spot in the galactic outskirts has likely been a steadier, more sheltered environment all these billions of years, giving life the time it needed to form, unfold, adapt, and slowly flourish in its own unhurried way. We're not living right in the center of galactic excitement. No, we're more in the cozy suburbs of the stars, a sort of peaceful neighborhood, far from any hectic cosmic downtown, where the lights are softer, the pace is slower, and everything has a bit more room to breathe. A calm little burrow of the universe, really, tucked just far enough away to be safe, stable, and wonderfully well placed for life to dream itself into existence, all spinning gently along as the stars shimmer quietly on above us, utterly unaware of the marvels they've helped make possible down here. But what really are these spiral arms we see stretching gracefully across the Milky Way? For much of the 20th century, astronomers found this quite the puzzler. If the arms were fixed, solid structures, like spokes on a wheel, the galaxy's rotation would have wound them up tightly long ago. In just a few 100 million years, they would have disappeared entirely. The answer, quietly elegant and rather surprising, came from thinkers like Bertil Lindblad and C.C. Lin. The spiral arms, they proposed, aren't permanent collections of the same stars drifting together. Instead, they are more like gentle patterns, soft, sweeping waves of density that move through the galactic disk. Imagine it like ripples moving through a pond. The water itself isn't traveling across the surface in the same way the ripple is, yet the pattern glides steadily along. In the same way, stars drift in and out of these spiral waves, carried gently by the galaxy's rotation, while the arms themselves maintain their graceful form. It's a quietly beautiful solution, a reminder that the galaxy's most striking features are often not solid or fixed, but flowing, shifting, and alive with gentle motion. Picture, if you like, a gentle traffic jam on a long motorway. The jam itself is really just a pattern, a region where the cars are more tightly packed, and it can move along the road even though the individual cars are always entering and leaving. Cars slow down, bunch together, then drift away, and yet the jam itself lingers, carrying on as a kind of living pattern. The spiral arms of the galaxy work in much the same way. They are waves of slightly higher density, gently moving through the disk, while the stars and clouds of gas drift in and out of them at their own pace. When a cloud of interstellar gas enters one of these arms, it feels a subtle squeeze from the extra gravitational pull of the wave. That gentle compression nudges portions of the cloud to collapse, and new stars begin to form. The most massive of these new stars shine brightly in brilliant blue, lighting up the spiral arm like a string of lanterns and tracing out the graceful pattern for us to see. In a few million years, these young blue giants exhaust themselves in quiet, dramatic bursts, supernovae, while the remaining stars, now older and redder, drift slowly out of the arm on the far side. And yet, the spiral pattern persists. It's illuminated by a constantly changing population of stars, each one taking its turn in the quiet, ongoing cycle of birth and death. A slow, cosmic dance, graceful, patient, and endlessly renewing, giving the galaxy its elegant, luminous form. A quiet rhythm of creation and fading, endlessly unfolding above us, like a lullaby written in starlight. This grand, slow dance of the galaxy is set to the music of gravity, and in a way, we can see that music reflected in the journey of our very own sun. Our solar system doesn't simply trace a neat, circular path around the galactic center. Instead, as it sweeps along at a breathtaking 230 kilometers per second, that's some 828,000 kilometers an hour, it also gently bobbles up and down through the plane of the disk. It's rather like a carousel horse on a merry-go-round, not only spinning around, but rising and dipping in a quiet, steady rhythm. One complete up and down cycle takes about 60 to 70 million years, a slow, majestic oscillation that carries the sun above the plane, down through it, below it, and then back up again. Some paleontologists have even noticed an intriguing, if still debated, pattern, roughly every 62 million years, that appear to be subtle pulses in Earth's biodiversity and extinction record. The idea is that as the sun drifts through different regions of the galactic disk, the density of interstellar gas and dust changes ever so slightly, which could influence the flow of cosmic rays reaching our little planet. Those cosmic rays might then play a quiet role in cloud formation and climate, nudging life here in gentle, imperceptible ways. It's a profound, almost poetic thought that the vast, majestic rhythm of the Milky Way itself might have whispered guidance to the story of life on Earth. A quiet, cosmic conductor playing a soft, endless symphony while we spin along within it. And so, our first quiet drift through the outer and middle reaches of our galactic home comes to a gentle close. We felt the subtle, unseen tug of the dark matter halo, wandered among the oldest stars, true fossils of the early cosmos, and glimpsed the soft traces of galaxies long since absorbed into the Milky Way's embrace. We've come to understand the spiral arms not as fixed structures, but as flowing, living patterns guiding the slow, graceful cycle of stellar birth and death. And here, in the calm of the Orion Spur, we found our own little corner, a serene and sheltered nook, a quiet testament to the pockets of stability that can exist even within a universe that is otherwise vast, dynamic, and often violent. A gentle, cosmic reminder that amidst all the motion and change, there are still places of calm, stillness, and quiet beauty, and that, perhaps, is exactly where we belong. But our journey is far from finished. The grandest mysteries and the most awe-inspiring landscapes still lie ahead. From our quiet little suburban arm, we'll drift gently inward towards the bustling, crowded, and endlessly intriguing heart of the Milky Way. Along the way, we'll pass through glowing nebulae, where new stars are quietly coming to life, and through regions of intense, almost unimaginable energy, where stars reach the end of their brilliant lives. And finally, we'll approach the very core itself, a place dominated by a silent, sleeping giant, whose presence quietly guides the motion of billions of stars around it. It's a journey that moves us both towards the light and into the soft, deep shadows at the very center of the galaxy. A voyage of wonder, calm, and slow, celestial rhythm, inviting us to simply float, observe, and marvel. The space between the stars is not quite as empty as it might first appear. As we drift further from the familiar glow of stellar nurseries and the soft, fading light of planetary nebulae, the character of the galaxy's light begins to change. The crisp, dark void, sprinkled with distant pinpricks of starlight, slowly softens into a gentle, pervasive glow. We are now entering the more densely packed regions of the inner galactic disk, where billions of stars gather close enough that their combined light blends into a kind of luminous mist. The distance between stars shrinks dramatically. Out near our sun, we enjoy a peaceful kind of solitude, over 4 light years separating us from our nearest neighbor, Proxima Centauri. But here, in the inner reaches, stars might lie only a few trillion miles apart, practically a stone's throw in cosmic terms. Imagine a planet circling one of these stars. Its night sky wouldn't be the deep darkness we are used to. Instead, it would be bathed in a soft, unending twilight, illuminated by the combined glow of thousands of suns, each shining as brightly as Venus does to us. The sky alive with light, gentle and continuous, wrapping the world in a warm, cosmic embrace. This growing crowd of stars is our first hint of the immense gravitational force we are now approaching. It's a quiet, almost invisible power, yet one that has shaped not just the orbits of countless stars, but the very structure of this central region itself. To truly understand this heart of the galaxy, we need to look past a veil that kept it hidden from human eyes for so very long. For centuries, astronomers gazing toward the constellation Sagittarius, where the galactic center resides, were met with an impenetrable barrier. This was no simple shadow. It was the Great Rift, a vast complex of dark nebulae so dense with cosmic dust that they swallow virtually all visible light from the stars beyond. It's as though the core of the Milky Way is tucked behind a range of immense, silent mountains, concealing its brilliance from our view. A shadowy, mysterious frontier, quietly holding the secrets of the galaxy's deepest heart, inviting us to imagine what lies beyond. The breakthrough came when we learned to see the galaxy in a different kind of light. Back in the 1930s, a young radio engineer named Karl Jansky, working at Bell Telephone Laboratories, was investigating the mysterious static that interfered with transatlantic radio signals. To his surprise, he noticed a steady, faint hiss drifting slowly across the sky. It didn't follow the sun or the weather or anything familiar. it moved in step with the rotation of the Milky Way itself. Jansky had, quite unintentionally, discovered radio waves streaming from the very heart of our galaxy. This was the quiet birth of radio astronomy. It showed that while the dense clouds of cosmic dust block visible light, the longer, gentler waves of radio could slip through unimpeded, like a deep, resonant voice passing effortlessly through a wall that would silence a whisper. The galaxy began to speak to us in a language we had never heard before. Over the decades that followed, radio telescopes around the world, from the Jodrell Bank Observatory in England to the Parkes Observatory in Australia, began to map this hidden, enigmatic heart of the Milky Way. What they revealed was both strange and awe-inspiring. Vast, expanding shells of gas appeared, the remnants of ancient supernovae, exploding far more frequently here than in the gentle suburbs where our sun resides. There were delicate, filamentary structures too, long, magnetized strands of energetic electrons stretching hundreds of light years, their origin still a quiet mystery. Amidst all this, astronomers found incredibly bright, compact sources of radio emission. The most prominent of these was given a name that hints at both its location and its elusive, enigmatic nature: Sagittarius A, a calm, unseen giant, quietly holding the galaxy together, revealing itself not in the harsh glare of visible light, but through the soft, penetrating whispers of radio waves, a hidden heart, slowly letting us understand the rhythm of the Milky Way's very core. The A in Sagittarius A marked it as the brightest radio source in the constellation of Sagittarius, while the little asterisk was added later, following a convention in physics to indicate an excited state. And truly, it has proven a perfectly fitting symbol. Sagittarius. A star is the dynamic, restless heart of our galaxy, alive with unseen energy, yet hidden from ordinary sight. For many years, its true nature remained a profound mystery. Then, in the 1990s, a remarkable endeavor began. Astronomers Reinhard Genzel and Andrea Ghez led a team determined to do something almost unimaginable, not just to detect the radio waves from this invisible heart, but to observe the stars dancing in its immediate vicinity. Using powerful new instruments on giant telescopes in Chile and Hawaii, they turned to infrared light, the same quiet kind of light that, like radio waves, can slip through the thick clouds of interstellar dust. Slowly, carefully, over years of patient observation, they traced the motions of these stars, tiny cosmic dancers orbiting a presence far too massive to be anything other than extraordinary. A whisper of movement in the darkness, a hint of something immensely powerful, yet silent, at the very center of our galaxy. For more than 20 years, these astronomers patiently followed the paths of a group of stars known as the S stars as they whirled around the invisible center of the galaxy. To do so, they used a remarkable technique called adaptive optics. By projecting a laser into the upper atmosphere, they created an artificial guide star that allowed the telescope to correct for the blurring effects of Earth's air in real-time, giving them an astonishingly clear view. The results, published in journals like the Astrophysical Journal and Nature, were quietly breathtaking. One star, now called S2, was seen completing a full orbit in just 16 years. At its closest approach, it came within a mere 17 light hours of Sagittarius A star, closer than Pluto ever comes to our Sun, and it was moving at a staggering 2.5% of the speed of light, almost 5,000 miles every single second. It's a humbling and gentle reminder of the incredible forces at work in the heart of our galaxy, and of the patience and care it takes to witness them. By carefully applying Kepler's laws of planetary motion to the orbits of these stars, the astronomers arrived at a conclusion that was both inescapable and profoundly striking. The object at the very heart, Sagittarius A star, must contain a mass of roughly 4.1 million times that of our Sun. And yet, this vast mass is squeezed into a space smaller than our own solar system. There is only one kind of object in the universe that could hold so much matter in such a tiny volume: a supermassive black hole. A silent, invisible giant, quietly shaping the motions of stars around it, holding the very heart of the Milky Way together. A presence both terrifying and awe-inspiring, yet utterly serene in its immense cosmic patience. This remarkable discovery earned Reinhard Genzel and Andrea Ghez the 2020 Nobel Prize in Physics. And it forever changed the way we understand the hearts of galaxies. We now know that such colossal black holes are not rare curiosities. They seem to sit at the center of nearly every large galaxy, from gentle spirals to vast ellipticals. They are, in a very real sense, fundamental to the architecture of galaxies themselves. Our own Milky Way hosts its local example, Sagittarius A, pronounced Sagittarius A star. For now, it is comparatively quiet, calm, and unobtrusive. Yet this calm is a kind of quietude that can be misleading, for even in its stillness, it commands immense power and influence over everything that orbits near it. A black hole is a place in space where gravity becomes so overwhelming that nothing, not even light itself, can escape. The boundary marking this point of no return is called the event horizon. 4. Sagittarius. This horizon would span roughly 24 million kilometers across, about 17 times the diameter of our Sun. It is a sphere of utter blackness, a one-way membrane from which no information can ever return. Close to this invisible boundary, the laws of physics take on a remarkable character. Space and time themselves are warped to extraordinary degrees, as described by Einstein's general theory of relativity. For an observer falling toward the black hole, time would appear to slow almost to a crawl compared with the rest of the universe. A place where the very fabric of reality seems to stretch and bend, serene, silent, and unimaginably powerful. The quiet nature of Sagittarius A comes from a simple reason. It isn't being fed very much. In a sense, it's starved, with little material falling into it. Yet it is not completely dormant. In 2019, and again in 2022, the world was treated to its first, blurry but profoundly revealing images of this cosmic giant's shadow. The Event Horizon Telescope, EHT, a remarkable collaboration linking radio observatories across the globe into a single Earth-sized virtual telescope, captured the glowing swirling ring of superheated gas and dust orbiting the black hole's event horizon. The images revealed a bright, slightly uneven ring, the photon sphere, where light itself traces precarious orbits around the black hole, encircling a dark central shadow, the silhouette of the event horizon. It was a breathtaking confirmation of Einstein's predictions and a triumph of human ingenuity, giving us, for the very first time, a direct glimpse of a black hole's mysterious, invisible heart. Even at its current, relatively gentle pace, the feeding of Sagittarius A is far from smooth. gas and dust don't simply fall straight in. Instead, they form a vast, hot, swirling accretion disk, where friction and magnetic forces heat the material to millions of degrees, causing it to blaze in X-rays. NASA's Chandra X-ray Observatory has caught frequent, unpredictable flares from this cosmic giant, sudden brightenings that last a few hours. These flares are thought to arise from hotspots, clumps of gas heated to extraordinary temperatures as they are stretched and torn by the black hole's immense tidal forces. Magnetic field lines may also snap and reconnect in a process similar to solar flares, but on a scale so vast it is almost unimaginable. It is a quiet yet restless heart, a place of intense energy and motion hidden behind the serene blackness we perceive from afar. The reach of this supermassive black hole extends far beyond its immediate surroundings. It serves as the primary gravitational anchor for the central bulge of the Milky Way, a region spanning thousands of light years. This bulge is far more intricate than the simple sphere of old stars astronomers once imagined. Observations in infrared light, particularly from NASA's Spitzer Space Telescope and the Wide Field Infrared Survey Explorer, WISE, have revealed a remarkable shape. From the side, the bulge resembles a giant peanut or an egg-shaped structure. This boxy or peanut bulge is now understood as a natural outcome of the dynamics of the galaxy's central bar, a subtle but profound reminder of how gravity and motion sculpt the very structure of our home galaxy, even on grand, thousands of light-year scales. The galactic bar. Another elegant layer of complexity in the heart of the Milky Way. Our galaxy is not a simple spiral, it is a barred spiral. Stretching across the center is a vast, elongated structure made up of billions of stars, some 27,000 light-years from end to end. This bar rotates almost like a solid body, and its gravitational pull acts as a kind of cosmic engine, gently funneling gas and dust from the outer disk toward the very heart of the galaxy. In other galaxies, or perhaps in our own distant past, this inflow can feed the central black hole, sparking periods of remarkable activity. The bar's rotation also plays a subtle but crucial role in shaping the bulge. Through a gravitational choreography known as orbital resonance, stars receive regular nudges that lift them into elongated orbits, gradually building the peanut or egg-shaped three-dimensional structure we observe. A quiet, intricate dance of stars unfolding over millions of years, sculpted by the unseen hand of gravity. If you imagine drifting just a few hundred light years from Sagittarius A star, the surroundings become some of the most extraordinary in the galaxy. It's not just those remarkable S-stars racing about. There's an entire neighborhood teeming with rather exotic remnants. You've got neutron stars and smaller black holes here too. All that's left of once massive stars that lived fast and burned brightly in this busy region before winking out. And according to careful studies, quite a few of those black holes seem to have slowly spiraled inward over time, gravitating toward the center like the heaviest shells settling to the bottom of a gentle tide. A sort of quiet, cosmic sorting, if you will. Nature simply nudging the most substantial things ever closer to the heart. And then, slightly farther out, there are the Fermi bubbles, one of space's most curious spectacles. They're enormous, hourglass-shaped clouds of ultra-hot gas stretching tens of thousands of light years above and below the entire galactic center, glowing faintly with high-energy light. We can't see with our eyes, but no is there all the same. A bit like deep ocean currents beneath a calm, moonlit sea. Their beginnings are still a bit of a puzzle, which is part of what makes them so captivating. Some believe they may be echoes from a dramatic period long ago when Sagittarius A star was far hungrier than it is now, drawing in matter with wild abandon and releasing astonishing bursts of energy in the process, enough to puff out clouds this vast. Others think they formed from many stars erupting in unison, a great collective outpouring of energy sweeping gas outward like the faint reverberation of fireworks viewed from miles away, softened by time. Whichever story is true, the Fermi bubbles linger as a reminder of a stormier age for our galaxy, an era when the center flared with a brilliant, untamed force. And yet, here we are now, billions of years on, witnessing only the quiet afterglow. The universe's louder chapters dimmed to whispers, easing us toward wonder rather than fear. A rather lovely thing, really. Even the most dramatic tales, when read by time, become gentle enough for drifting off to sleep. It's a feeling that science fiction explores rather beautifully, giving emotion and shape to things that might otherwise feel too vast to hold in the mind. In Doctor Who, for example, there's that lovely recurring notion of silent universes and the end of time, where the final flickers of reality simply cling on as everything else slips into stillness. Of course, it's all wonderfully imaginative, but underneath the whimsy, it touches a very real human worry, the fear of being alone in a universe slowly dimming, stretching out, and running colder with time. And in an odd way, our own galaxy tells a similar story. To picture its center once blazing like a quasar, breathtakingly bright and fearsome, and then to realize it has settled into quiet. Well, it's like watching grand bonfires become low embers at the end of a long evening. There's a melancholy to it, yes, but also something reassuring. The cosmos has its dramatic youth, its roaring middle age, and then, eventually, a softer calm. And we're part of that very same unfolding tale, however small we might feel in comparison. And it's rather heartening to know that the study of this region brings so many minds together. The international effort behind the Event Horizon Telescope involves places like the Harvard-Smithsonian Center for Astrophysics, the Max Planck Institute for Radio Astronomy, and the National Astronomical Observatory of Japan, all working in quiet harmony, like musicians tuning into the same distant melody. Meanwhile, the star-mapping brilliance of Gaia mission feeds into that picture too, joined by the steady eyes of ground-based observatories such as the Very Large Telescope and W.M. Keck Observatory. It's a proper worldwide effort, really. Scientists across continents passing data back and forth, little threads of light and measurement weaving into a shared map of home. And when you consider it like that, not as numbers and distances and violence, but as people peering upward from all over the earth, gently piecing together the story of the Milky Way, it becomes something far softer than intimidating. It becomes curiosity, connection, a lullaby written in stars and shared by the whole world. And that's rather lovely to rest with, if you ask me. As we sit with that dark, quiet sphere at the center of it all, it gently nudges us toward one of physics' deepest puzzles, something rather poetically called the information paradox. It was Stephen Hawking who first sketched out the problem, wondering what becomes of information, the tiny quantum details that make every particle of matter utterly unique once it slips past the point of no return. He discovered that black holes might slowly fade over time, emitting a soft shimmer known as Hawking radiation, predicted to eventually make them evaporate altogether. But here's the curious bit. His maths hinted that the information carried by everything that falls in might simply vanish, and that doesn't quite sit right with the rules of quantum mechanics, which insist information can't ever truly be destroyed. It's a bit like posting a letter into a locked box and then being told the words inside it cease to exist. Rather unsettling for the poor postmaster, you'd imagine. So we're left with this gentle but stubborn disagreement between two towering ideas, Einstein's relativity and the strange, shimmering dance of quantum physics. It's one of science's great unsolved riddles, not loud or frantic, but beautifully persistent, like a question whispered that refuses to quite drift away. To make sense of it, scientists have explored some wonderfully imaginative notions. One of the favorites is the holographic principle, which suggests that the story of everything that tumbles into a black hole might be delicately inscribed along its surface, the event horizon, in just 2 dimensions, rather like music stored on an old CD. Except, of course, this one would be cosmic in scale, larger and cleverer than any disk we could hold in our hands. Papers exploring these ideas have appeared in journals like Physical Review Letters, alongside other delightfully mind-bending theories, including the idea that the universe itself might behave a bit like a hologram, storing its information along boundaries rather than in volumes. And when you think of the black hole at the heart of our galaxy, that lovely shadowed Sagittarius A, quietly sitting, gently glowing now and then with a flare or a wobble of gas, it feels almost like an invitation, not something to fear, but something to marvel at. A reminder that even in the galaxy's stillest places, there are soft, shimmering questions waiting, and humans all over the world leaning in ever so gently to listen. From the wild, brilliant turbulence where stars are born, right through to the calm, velvet darkness of the event horizon, our little voyage inward has offered a glimpse of the entire cosmic spectrum. We've watched the galaxy knitting itself together, and at times pulling itself apart again, crafting the very elements of life inside stellar furnaces, scattering them across space in bursts of supernova fire, all the while guided by that immense gravitational anchor sitting quietly at the center. Along the way, we've drifted from chemistry to physics, and then into something even grander, spacetime itself, where the familiar rules bend into something gentler, stranger, and full of wonder. And now, as we ready ourselves to look outward once more, pondering the Milky Way's place in the wider universe and where it might eventually be headed, we carry with us this rather humbling thought. We are, quite literally, made from all of it. Every quiet miracle, every blazing eruption, every invisible pull of gravity that shaped our home long before we ever knew to name it. We're the universe, waking up just enough to observe itself, peering back from a small, rocky little world tucked away in the quieter neighborhood of a spiral galaxy, curious, thoughtful, and gently daring to understand that silent, spinning heart at the center of it all. And isn't that something rather lovely to drift off with? Having spent a little while lingering near the quiet, heavy heartbeat at the center of our galaxy, feeling the immense and rather mysterious pull of Sagittarius A, It's time now to gently turn our gaze back outward, but we won't simply drift straight back to our cozy little corner in the Orion Spur just yet. Instead, let's imagine ourselves rising, slowly, softly, away from the galactic plane, floating upward like a leaf caught in a calm night breeze. From up here, the Milky Way wouldn't be a swirl we're moving within, but a great luminous spiral laid out before us in full. A quiet, starlit island seen from afar, beautifully structured, endlessly patient in its turning. And this is the moment where we place that graceful spiral into its larger home, nestled among the long archipelago of the universe itself. Because our galaxy, as vast as it feels when you're inside it, is only one chapter in a much bigger story. A story that began billions of years before us and will carry on for billions more. And somewhere right in the middle of it all is this tiny, gentle moment we occupy now. Brief, extraordinary, impossibly beautiful, where the universe pauses just long enough for us to look back, wonder a bit, and feel connected to the whole magnificent design. A rather lovely thought to hold as you begin to drift off, isn't it? As we drift gently upward, the twinkling spiral arms we know so well start to blur into one rather gorgeous, glowing disk, a quiet whirl of countless suns set against the deep, restful black of space beyond. From this vantage point, we can take in something quite comforting, really. Our galaxy isn't by itself after all. It's part of a little family. Astronomers call this family the local group, a small gathering of galaxies held together by gravity, calmly moving outward with the ever-expanding universe. It's not the biggest family, mind you, just over 50 known members or so, but it's ours. And there's something rather sweet about that. At the heart of it sit the two heavyweights, the Milky Way, of course, and our nearest major neighbor, the Andromeda Galaxy. You might have heard it referred to as M31, though for many years it carried the rather poetic title of the Great Andromeda Nebula, because for the longest time, no one quite realized what it truly was, just a soft, misty smudge of light hanging quietly in the night sky. It wasn't until the 1920s that Edwin Hubble, working at Mount Wilson Observatory, trained the mighty 100-inch Hooker telescope toward it and made a discovery that quite changed everything. He managed to pick out individual stars, called the Cepheid variables, nestled within Andromeda's spiral arms. These stars flicker in brightness with a steady rhythm, and by tracking that rhythm, Hubble worked out just how luminous they truly were, and how far away they must be for us to see them so faintly. The answer? Far beyond our own galaxy, nearly 1 million light-years distant. In that moment, the universe became much larger than anyone imagined. The Milky Way lost its title as the whole of existence, and instead became one beautiful home among many. And rather than making us feel small or isolated, it reminds us we belong to something bigger. A quiet little neighborhood woven into a truly endless sky. A rather lovely thing to ponder as you snuggle in and let sleep gently carry you along, wouldn't you say? The third largest in our little local family is M33, or the Triangulum Galaxy, if you prefer something a bit more lyrical. A gentle, face-on spiral that looks almost like it's quietly smiling up at you from afar. And then, of course, there's the rest of the crowd, a whole collection of much smaller galaxies that hum along with us in the same slow cosmic tide. The most noticeable of them, are the large and small Magellanic Clouds, two soft, glowing companions visible from the southern half of the world, sitting nearby like little lanterns hung just off the Milky Way's edge. Astronomers have also found plenty more in the mix, smaller, quieter ones, such as the Sculptor Dwarf and the Fornax Dwarf, as well as the Leo and Leo II systems. These little galaxies aren't grand and shimmering like Andromeda or Triangulum. They're faint, delicate collections of stars, wrapped quietly in their own cocoons of dark matter, almost like drifting clouds of stardust themselves. For many years, scientists imagined these dwarf galaxies had spent most of their long lives in gentle, steady orbits around the Milky Way, strolling around it like familiar, predictable companions. But then along came the remarkably clever Gaia mission, quietly rewriting the narrative. With its beautifully precise measurements of stellar motion, it's shown us something rather surprising. A few of these smaller galaxies, the Magellanic Clouds among them, may well be making their very first grand approach toward the Milky Way. Not old neighbors after all, but curious newcomers drifting in from the darkness. And as they wander closer, their gentle gravitational pull seems to stir the dark matter halo, almost like a pebble plopped into a still pond. Their arrival might even be one of the reasons our own galactic disk has that graceful little warp to it, a subtle curve shaped by invisible threads of gravity stretching and tugging as these fresh companions join the fold. Not a disruption, really. More like a quiet ripple of connection, a slow cosmic hello whispered across space. A rather soothing thing to picture as the universe goes about its endless, gentle waltz. Don't you think? The local group, lovely and familiar as it is, isn't floating about on its own either. It sits on the gentle outskirts of something far, far larger, a grand structure astronomers call the Virgo supercluster. Picture hundreds of little galaxy families like ours, slowly gathering in the same enormous gravitational embrace, all being nudged toward a shared center, somewhere in the Virgo constellation. At the very heart of that region lies M87, a giant elliptical galaxy, quiet and powerful in its own right, home to the first ever black hole humans managed to capture an image of, thanks to the clever people behind the Event Horizon Telescope. A rather historic moment, really, and one that reminds you just how patient and curious we can be when we set our minds to understanding the universe. In that greater cosmic neighborhood, our own galaxy family is a bit like a peaceful suburban outpost, resting quietly on the fringes, gradually feeling a faint but steady pull toward the more crowded Virgo cluster over hundreds of millions of years. No rush, no hurry, just the slow rhythm gravity likes to keep. And even that immense supercluster is only part of something larger still, an even grander gathering known as the Laniakea supercluster, named in Hawaiian to mean immeasurable heaven. I quite like that name, actually. It gives the whole thing a softer, human warmth, even though we're speaking of scales almost impossible to picture. It's defined not by walls or borders, but by the subtle flow of galaxies, like cosmic streams, quietly leading into one another. And when you step back and look at it all, there's this rather elegant order to things. Stars gather to form galaxies. Galaxies gather into groups like the local group. Those groups form clusters, then superclusters. All of it woven together in a massive, shimmering cosmic web that spans the part of the universe we know. Not a lonely picture at all, really. More like a quiet reminder that everything, from the tiniest mote of dust to the grandest swirl of suns, is part of the same incredible tapestry, calmly unfurling, endlessly turning, softly shining back at us as we, for now, simply rest beneath it. And this leads us to one of the most interesting stories our little cosmic neighborhood has left to tell: the future of our two large spirals. For the longest time, no one could say for sure whether Andromeda was drifting toward us or simply sliding past. Its light carries a subtle blue shift, the wavelengths ever so slightly compressed, which does, quite helpfully, tell us it's moving in our direction. But the lingering question was always this: is it heading straight for us, or merely wandering sideways along some much larger orbit? It took years of careful study, using the wonderfully patient eye of the Hubble Space Telescope to finally settle the matter. Then, in 2012, Roland van der Marel and his team managed to measure Andromeda's sideways movement across the sky with a precision that would make even the calmest scientist a bit giddy. And what they found was, well, decisive, really. The tangential motion was simply too small to avoid a direct encounter. So, rather famously now, we know this: the Milky Way and the Andromeda Galaxy are on a gentle but certain path toward one another, a slow-motion meeting written into their orbits long before humans ever thought to look up and wonder. A collision, if you like the technical term, but there's no need to clutch your pearls. It's still billions of years away, unfolding at the serene pace gravity always seems to prefer. A rather extraordinary future, quietly humming along while we, for now, simply breathe and rest. Let us take a moment to truly feel the scale of what is coming. This is no mere celestial nudge or passing brush. We are speaking of a slow, majestic dance, the gentle, inexorable merging of two galactic titans. It is a process that will reshape the night sky for anyone watching from within either galaxy, and will eventually forge an entirely new kind of galaxy from their combined matter. The timeline is so vast, it almost defies comprehension. The first close encounter is expected in roughly 4.5 billion years. Even before stars from each galaxy collide, gravity will begin its subtle, relentless work. Tidal forces will tug at stars, gas, and dust, stretching them into long, luminous bridges and sweeping tails that extend across hundreds of thousands of light years. The elegant spirals we now take for granted will be unraveled, their familiar shapes dissolved into a cosmic tapestry of motion and light. It is a slow, cosmic symphony, written in the language of gravity, patience, and time itself. In the night sky of a far distant Earth, the approach of Andromeda would be a sight of awe-inspiring, almost overwhelming beauty. What begins as a faint, delicate smudge would gradually swell into a brilliant, sweeping band of light, eventually rivaling and then outshining the Milky Way itself. The heavens would shimmer with a dizzying multitude of stars. And yet, within this apparent chaos lies a quietly reassuring truth. The chance of any two stars actually colliding is vanishingly small. The distances between them are so vast that the galaxies will pass through one another almost effortlessly, like two swarms of fireflies brushing past in the night, each individual star untouched. The story is different for the immense clouds of gas and dust that thread through both galaxies. When these vast clouds meet, they will collide with tremendous energy, sending shockwaves rippling through space. And from this cosmic turbulence will will spring a spectacular bloom of new stars, a dazzling starburst that will set the galaxies alight with the radiant blue-white glow of millions of newborn suns. This first encounter will not be the final act. The two galaxies, now entwined in a slow, gravitational dance, will swing past one another, drift apart, and then fall back together for a second, even closer embrace. Over the course of another 2 or 3 billion years, they will finally merge into a single, entirely new galaxy. What might this new entity look like? Supercomputer simulations, using programs with names like GADGET and AREPO, give us a glimpse, as described in journals like Science. The graceful spiral arms we know so well will vanish. In their place will be a vast, smooth, and gently rounded galaxy, an elliptical galaxy. The carefully ordered rotation of the original disks will be replaced by a swarm of stars moving on tangled, plunging orbits. This future galaxy, a union of our Milky Way and Andromeda, is affectionately dubbed Milkdromeda. And what of the central black holes? Sagittarius A star, and Andromeda's own supermassive black hole, weighing in at over 100 million times the mass of our Sun, will also be drawn together. Slowly, pulled by the gentle tug of dynamical friction, they will sink toward the heart of Milkdromeda, forming a binary pair that twirls around each other in a dizzying cosmic dance. Their motion will stir the surrounding stars, sending some hurtling away on extraordinary hypervelocity journeys, cast out by gravitational slingshots. In time, over billions of years, the two black holes will finally merge. This cataclysmic union will ripple across the cosmos, sending a titanic burst of gravitational waves that stretches and shakes the very fabric of spacetime. Future observatories, like the European Space Agency's LISA mission, a space-based gravitational wave detector with NASA participation, are designed to witness such extraordinary events, connecting us, in imagination, to the earliest, most dramatic epochs of the universe. This cosmic destiny feels both dramatic and final, a fitting conclusion to the long lives of two magnificent spirals. Yet, it is not the end of the story for the local group. As the Milky Way and Andromeda merge, they will gradually draw in the smaller, surrounding dwarf galaxies. The Magellanic Clouds, the Triangulum Galaxy, and all the faint, wispy satellites will eventually be absorbed, their stars joining the vast, smooth halo of the newly formed elliptical. The local group will transform, condensing from a collection of distinct islands into a single, immense galactic continent, adrift in the quiet, expanding void. This grand narrative of galactic evolution, from pristine disks to a merged elliptical, is a key prediction of modern cosmology. We see it unfolding elsewhere in the universe. The Hubble and James Webb Space Telescopes have captured breathtaking images of galaxies in the midst of merging, their shapes stretched and twisted into strange, beautiful forms. The Antennae galaxies, the Mice galaxies, offering a preview of our own distant future. There is a quiet poetry in this. It touches on a theme often explored in human storytelling, the cyclical nature of existence, of endings and new beginnings. In Lars von Trier's film Melancholia, the approach of a rogue planet serves as a metaphor for an inevitable end. In the cosmos, Andromeda's approach is similarly unavoidable, yet it is not an ending, it is a transformation. The galaxy is recycling itself, giving birth anew in a different form. The stars will endure, shining on, even as the familiar structure of the Milky Way dissolves into something entirely new. It invites us to pause and reflect on our place in the vast stretch of cosmic time, we are fortunate, in a very special way, to be living right now. Tonight, the sky still holds its deep darkness. The Milky Way stretches across it like a luminous flowing river, and Andromeda remains a distant, intriguing mystery. In a few billion years, this sight will change beyond recognition. We are also living in an age when the universe itself is still bright and open, sprinkled with countless stars. Observations from telescopes like the James Webb suggest that the universe's most vigorous era of star-making is already behind us. We are, in a sense, in the cosmic afternoon. As the universe stretches outward, driven by the quiet but relentless push of dark energy, galaxies will drift ever further apart. The materials for new stars will be locked away in old stellar remnants and scattered gas, and the universe will slowly grow darker, cooler, and quieter. It's a gentle reminder of the rarity of this moment and how privileged we are to witness the cosmos in all its present glory. Our very ability to understand this vast, unfolding story is a quiet testament to centuries of human curiosity and endeavor. It's a tale woven together by the careful, patient work of countless individuals across different cultures and generations. From the early star catalogues of the Babylonians and Greeks to the revolutionary ideas of Copernicus and Galileo, to the detailed photographic surveys at Palomar, and on to the exquisite precision of space telescopes like Hubble, Gaia, and Webb. Each generation has quietly built upon the discoveries of those who came before, slowly refining our sense of where we sit in the cosmos. Even the newspaper headlines we read: Hubble proves universe is expanding, COBE satellite maps, Big Bang's afterglow, first image of a black hole, are just chapters in this single, ongoing story of human wonder. It's a gentle reminder that our understanding of the universe is a shared gift, a legacy of curiosity stretching back through time, patiently guiding us to see a little more clearly each day. As we draw this part of our journey to a close, drifting gently above the future side of this galactic meeting, there's a feeling that is at once humbling and quietly profound. The very atoms that make up our bodies were born in stars that shone and faded long before the Milky Way took the shape we know today. They were part of the endless cycle of birth and death in those swirling spiral arms, eventually gathering into the clouds that collapsed to form our sun and the planets around it. In the most literal sense, we are stardust, and now, remarkably, we are conscious stardust. We are the universe's way of glimpsing itself. We have learned the mathematics to trace the paths of stars orbiting an invisible giant some 26,000 light-years away. We have built instruments capable of seeing the faint afterglow of creation itself. We can even foresee the destiny of our galaxy, billions of years into the future. It is a quiet, extraordinary gift to know that in observing the cosmos, we are, in a sense, the cosmos itself, awake and aware. The Milky Way is our home, not just in space, but in time. It has offered a steady, enduring stage for life to evolve over billions of years. Its quiet spiral arms, its gentle rhythm of star formation, and the protective embrace of its dark matter halo have all come together to create a corner of the cosmos where a curious species could emerge, look up at the stars, and begin to tell their own story. A story of immense power and delicate grace, of quiet moments and bursts of violence. A story that continues to unfold even now. And for this fleeting, luminous moment in cosmic history, we are here to witness it. We have drifted across the silent ocean of the dark matter halo, watched the life cycles of stars in the spiral arms, stood in awe before the darkness of the galactic core, and glimpsed billions of years into a future shaped by cosmic collision. Yet, in truth, our journey has only just begun. We have spoken of the galaxy as we can see it, as our telescopes can map it, and as our physics can measure it. But now it is time to venture further, into the deeper shadows, into the realms of what we cannot yet see and what we do not yet understand. This is the frontier of modern galactic astronomy, a place where theory meets baffling data, and the most profound questions about the nature of reality remain wide open. And so, we arrive at perhaps the greatest mystery of all, the ghost that quietly holds our galaxy together: dark matter. We know it must be there. We feel its presence in the cosmic dance, yet its true nature eludes us. All we can trace is its gravitational signature, in the rotation of galaxies, the bending of light around clusters, and the vast scaffolding of the universe itself. It outweighs the matter we are made of by 5 to 1. It dominates the cosmos, and yet, for nearly a century, it has remained invisible to every attempt to detect it directly. It is a quiet reminder that the universe still holds its secrets, waiting patiently for us to uncover them, one gentle discovery at a time. For many decades, the leading candidates for dark matter have been a curious type of particle known as WIMPs, or weakly interacting massive particles. These elusive particles are thought to be their own antimatter partners, interacting with ordinary matter only through the very subtle pull of the weak nuclear force and the gentle tug of gravity. Perhaps this is why they are so remarkably difficult to detect. Scientists have built extraordinary experiments in pursuit of these ghostly visitors. Deep beneath the Earth's surface, in places like South Dakota, the Large Underground Xenon Experiment, or LUX, and its successor, LUX Zeppelin, along with Xenont in Italy, sit patiently. They contain vats of ultra-pure liquid xenon, shielded beneath a mile of rock to keep out cosmic rays, waiting for the tiniest of signals, the faintest nudge of a single xenon nucleus that might reveal a WIMP passing through. And yet, so far, they have been met with a profound, almost eerie silence. It is a quiet reminder that the universe can be infinitely subtle, and that sometimes the most extraordinary secrets lie in the stillness, waiting for us to listen carefully enough. This long, quiet silence has encouraged a thoughtful re-examination within the field. As noted in a major 2023 review in Nature, the possibilities for the classic vanilla WIMPs are narrowing, prompting a blossoming of new ideas. Some physicists, for instance, at the University of Amsterdam, are exploring fuzzy dark matter, ultralight particles called axions, so light that they behave like gentle waves stretching across entire galaxies. Others, at places like MIT and Harvard, are investigating far more intricate models, where dark matter might have its own hidden forces and particles, a kind of shadow universe that quietly coexists with our own, interacting only through the pull of gravity. Then there is the boldest idea of all. Perhaps dark matter isn't needed at all. This is the territory of modified Newtonian dynamics, or MOND, first proposed by Israeli physicist Mordechai Milgram in the 1980s. MOND suggests that our understanding of gravity itself might be incomplete. In the outer reaches of galaxies, where accelerations are tiny, Newton's laws may not quite hold, and gravity might follow a slightly different rhythm. Remarkably, this single adjustment can reproduce the flat rotation curves of galaxies without invoking any unseen matter. For its supporters, it is an elegant solution, yet it is not without its challenges. Mons struggles to explain the behavior of galaxy clusters like the Bullet cluster, where the bending of light suggests a dark matter halo was stripped away during a cosmic collision. The debate between Mond advocates and the dark matter camp remains one of the most impassioned in all of science, unfolding across journals, conferences, and the minds of those who ponder the universe's deepest workings. And just when it seems the mysteries might end there, they deepen with an even stranger force: dark energy. While dark matter pulls the cosmos together, dark energy quietly pushes it apart, driving the universe's accelerating expansion, a revelation that took the scientific world by surprise in 1998. The leading idea is that it is a property of space itself, what Einstein once called the cosmological constant. Yet when theorists calculate the vacuum's energy, the result is wrong by a mind-boggling factor of 10 to the power of 120, perhaps the most staggering error in the history of science. It hints at something profound we have yet to understand. Could dark energy be a dynamic field, shifting over time? Might it eventually reverse, leading to a big rip that tears the cosmos apart, or a big crunch that draws it all back together? Missions like the European Space Agency's Euclid telescope and the Dark Energy Spectroscopic Instrument, DESI, are now mapping the universe's expansion with extraordinary precision, seeking to uncover the nature of this dominant yet utterly mysterious force. It is a gentle reminder that the universe is a place of quiet wonder, full of secrets patiently waiting for us to notice. One careful, thoughtful observation at a time. These mysteries are not abstract ideas floating far from us. They are woven into the very fabric of our galaxy. The nature of the dark matter halo shapes how the Milky Way formed, and how it will one day meet Andromeda. The amount of dark energy in the universe dictates the ultimate fate of the entire local group, slowly isolating it in an ever-expanding void. We exist in the quiet intersection of these two profound unknowns. Let us drift closer to home for a moment, to a mystery that is both nearby and, in its own way, just as strange. For centuries, astronomers have noticed that our solar system seems curiously free from nearby supernova. We reside within a local bubble, a region of hot, diffuse gas roughly 1,000 light-years across, encased in a shell of cooler, denser gas and dust. But how did this bubble come to be? A groundbreaking study published in Nature in 2022 by astronomers at the Center for Astrophysics, Harvard and Smithsonian used Gaia spacecraft data to perform a kind of cosmic archaeology. By tracing the motions of nearby star clusters and interstellar clouds backward through time, they arrived at a remarkable conclusion. This bubble was carved out by a sequence of 15 to 20 supernovae, beginning some 14 million years ago and continuing over millions of years. The shockwaves from these consecutive explosions pushed the surrounding gas outward, inflating the very cavity in which our solar system now resides. It is a striking discovery, a reminder that our local stellar neighborhood has been shaped by violent, dynamic events, and that our position is only a fleeting moment in a constantly changing galactic environment. This leads us to yet another secret of the Milky Way, the missing satellite problem. According to supercomputer simulations of galaxies in a universe dominated by cold dark matter. Our galaxy should be surrounded by thousands of dwarf satellite galaxies. Yet so far, we have only found around 60. Where are the rest? There are two compelling possibilities. They may be so faint, so dominated by dark matter, that our current surveys simply haven't detected them. The Vera C. Rubin Observatory in Chile, beginning operations in 2025, will conduct a deep 10-year survey of the southern sky and is expected to uncover hundreds, perhaps even thousands, of these ultra-faint companions. The second possibility is more intriguing. The dark matter itself may be warmer and more fast-moving than we expected, preventing the formation of such small galaxies. Whether we find them or not will offer vital insight into the very foundations of particle physics and cosmology. And as we ponder these vast cosmic mysteries, it is worth remembering the human story behind them. Dark matter was first glimpsed not through grand machines, but through the keen eye of a solitary astronomer. In the 1930s, Swiss astronomer Fritz Zwicky at Caltech studied the Coma cluster of galaxies. He noticed the galaxies were moving far too quickly to be held together by visible matter alone. He proposed the existence of Dunkelmaterie, or dark matter, to explain the missing gravity. At the time, his idea was largely ignored. It wasn't until the meticulous work of Vera Rubin in the 1970s, who faced her own challenges in a male-dominated field, that the evidence became undeniable. Her measurements of galaxy rotation curves provided the definitive proof that something profound was missing from our understanding of mass. It is a gentle, humbling reminder that science does not progress through data alone, but through the curiosity, courage, and perseverance of those who dare to question the known and to look deeply at the universe with fresh eyes. The same is true when we turn our attention to the heart of our galaxy. For so long, the galactic center was a place of speculation, a mystery shrouded in shadows. The first hints arrived as whispers in radio static. The first real clues of a central black hole came from observing the motions of ionized gas. The definitive proof, however, emerged thanks to the remarkable dedication of two teams, led by Reinhard Genzel and Andrea Ghez. For more than 20 years, they patiently tracked the orbits of stars, carefully removing the blurring effects of Earth's atmosphere, month after month, year after year. Andrea Ghez has often spoken of the extraordinary patience this work demanded, watching data accumulate over many years before a single star had completed its orbit. This is not the instant gratification of a storybook. It is the slow, meticulous, and ultimately triumphant rhythm of real discovery. And in that patient observation, we find a quiet, profound reminder. The universe often reveals its deepest truths only to those willing to watch and wait with steadfast attention. And what of the explorers of tomorrow? The next generation of telescopes promises to reveal even more of our galaxy's secrets. The James Webb Space Telescope, with its extraordinary infrared sensitivity, is already peering through the dust at the galactic center, studying the population of faint, low-mass stars and probing how stars form in this extreme environment. Looking ahead, the Nancy Grace Roman Space Telescope, set to launch later this decade, will carry out a sweeping survey of the Milky Way, mapping billions of stars and perhaps even discovering thousands of distant exoplanets through the subtle dance of microlensing. On the ground, the extremely large telescope, with its impressive 39-meter mirror, will, by the decade's end, be capable of capturing the motions of stars so close to Sagittarius A that we may witness, almost directly, the gentle tug of general relativity, the slow precession of their orbits as they curve around the black hole. It is a quietly thrilling thought that the story of our galaxy continues to unfold, and that future eyes, both on Earth and in space, will allow us to see the universe in ways we have only dreamed of. We are living in a truly golden age of galactic discovery. Every mystery we solve seems to reveal two more in its place: the puzzle of dark matter, the enigmatic pull of dark energy, the history of our local bubble, the search for the galaxy's missing satellites. These are the great challenges that will shape astrophysics in the 21st century. They remind us to question the very laws of physics we thought we understood, and they remind us that the Milky Way, for all its beauty and grandeur, still holds profound secrets. It is a cosmic laboratory, both our home and our teacher, inviting us to look deeper, think harder, and imagine a reality far more wondrous than we have ever dreamed. We have wandered into the realms of dark matter and dark energy, confronting the unknown forces that shape the cosmos from the shadows. Yet the galaxy is not only a playground for physicists, it is also a canvas for chemistry, a cradle for biology, and a stage for the human drama of exploration and imagination. To truly know the Milky Way, we must now turn our attention to its intricate molecular tapestry, to the search for other worlds, and to the many beautiful ways we tell stories about our place in the universe. In this sense, we are moving from the architecture of the galaxy to its soul. Let us begin in the cold, dark clouds that drift between the stars. For much of history, interstellar space was thought to be a near-perfect vacuum, an empty stage upon which the stars performed. But we now know it is anything but empty. It is filled with the interstellar medium, a delicate, diffuse mixture of gas and dust, and within it, a complex, vibrant chemistry quietly unfolds. The story began in the 1960s, when astronomers detected mysterious radio signals that did not match any element known on Earth. These signals came from molecules, first hydroxyl, then, to the astonishment of scientists, water and ammonia. This marked the birth of astrochemistry. Today, thanks to radio telescopes like ALMA in Chile and the Green Bank telescope in West Virginia, we have detected over 200 different molecular species in the interstellar medium. The list is astonishing. From simple molecules like carbon monoxide, used to map the galaxy's structure, to complex organic compounds like ethyl alcohol in unimaginably vast quantities, glycolaldehyde, a simple sugar, and even amino acetylnitrile, a precursor to the amino acid glycine. The giant molecular cloud Sagittarius B2 near the galactic center is a particularly rich hotspot, a true factory of cosmic chemistry. How do these molecules form in the cold, sparse vacuum of space? Tiny dust grains act as cosmic catalysts. Atoms and simple molecules stick to these grains, gently losing energy as they move across the surface until they meet a partner. Hydrogen atoms combine to form H2. Carbon and hydrogen link to form complex chains, and the energy for these reactions comes from the soft warmth of starlight, or, more dramatically, from the shockwaves of nearby supernovae. This is not life, yet it is the raw, prebiotic chemistry from which life could emerge. When a new star and planetary system form from one of these clouds, the complex molecules are incorporated into the protoplanetary disk, and from there into comets, asteroids, and planets. The building blocks of life, it seems, are a natural and widespread byproduct of galactic evolution. A 2022 study in Nature Astronomy, using data from the Rosetta mission to comet 67P/Churyumov-Gerasimenko, confirmed the presence of glycine and phosphorus, reinforcing the link between interstellar chemistry and the ingredients necessary for life. It is a quietly wondrous thought that the very chemistry which makes life possible is not unique to our world, but drifts softly, invisibly, through the vast spaces between the stars, patiently waiting for the right conditions to awaken into life. This discovery subtly reshapes the way we see our galaxy. It is not a sterile collection of stars and gas. It is, in a sense, sprinkled with the potential for life. This idea was beautifully brought to life in the BBC documentary series The Planets, hosted by Professor Brian Cox. In the episode Life, Cox stands before a simulation of the early solar system, describing it as a soup of creation, enriched by complex molecules delivered by wandering comets. He says, in a tone of quiet wonder, the universe, it seems, is hardwired for chemistry, and perhaps for life. And this is not mere speculation. It is a conclusion drawn from careful observation and the steady work of radio astronomy. The natural next step in this story is one of the most thrilling quests of modern science: the search for habitable worlds beyond our own, for exoplanets. For centuries, planets around other stars were purely hypothetical. The first confirmation came in 1992, when planets were discovered orbiting a pulsar. But the real revolution began in 1995 with the discovery of 51 Pegasi b, a hot Jupiter orbiting a sun-like star, by Michel Mayor and Didier Queloz at the University of Geneva, work that later earned them the Nobel Prize in 2019. This was achieved through the radial velocity method, detecting the star's subtle wobble as the planet tugged gently on it. Then came NASA's Kepler Space Telescope, launched in 2009. Its mission was beautifully simple yet profound: to stare continuously at a patch of the Milky Way in Cygnus and measure the tiny rhythmic dimming of stars as planets passed in front of them. The results, published across journals like the Astrophysical Journal and Science, transformed our understanding. Kepler revealed that planets are not the exception, but the rule. There are more planets in our galaxy than stars. Small, rocky worlds like Earth and Venus are common, and many stars host planets within their habitable zones, regions where conditions might allow liquid water to exist. The numbers are staggering. Based on Kepler's data, astronomers at NASA's Ames Research Center estimate there could be as many as 40 billion Earth-sized planets orbiting in the habitable zones of sun-like stars and red dwarfs within our galaxy alone. Let that thought linger. 40 billion potential homes for life, just here in our Milky Way. It is a Copernican revolution on a galactic scale. We are not the center of the universe, and our little world is not a unique sanctuary. The baton has now passed to NASA's Transiting Exoplanet Survey Satellite, or TESS, which is surveying the entire sky to find the closest, brightest transiting exoplanets. And then there is the James Webb Space Telescope, JWST, a true leap forward. It is not merely finding planets, it is beginning to study them in exquisite detail. By observing the starlight that filters through a planet's atmosphere during a transit, JWST can detect the chemical fingerprints of gases like water vapor, methane, and carbon dioxide, and perhaps even combinations of gases that suggest life, such as oxygen and methane together. Already, the first atmospheric analyses of rocky, habitable zone planets are underway. Worlds like TRAPPIST-1e, an Earth-sized planet orbiting a cool red dwarf just 40 light-years away, are prime targets. A 2023 paper in Nature reported JWST's observations of the TRAPPIST-1 system, ruling out thick, hydrogen-rich atmospheres on some of the inner planets and paving the way for deeper studies of the outer, potentially more promising worlds. The search is no longer just for planets, but for living planets, for that first unmistakable sign that somewhere else, the galaxy's chemical predisposition for life has blossomed into biology. This grand quest is echoed in the storytelling of Apple TV Plus's acclaimed series For All Mankind. While dramatizing an alternate Cold War history, the show ultimately captures humanity's relentless drive to explore, to venture beyond our home world, a drive that is now, in reality, reaching for other star systems. It reminds us, gently but powerfully, of the emotional and imaginative weight of becoming an interplanetary species, a weight we are only beginning to understand. The discovery of cosmic chemistry and the abundance of exoplanets brings us back naturally to one of the most enduring questions. How did life arise on Earth, and how common or rare might it be throughout the galaxy? This is the domain of the rare Earth hypothesis, championed by paleontologist Peter Ward and astronomer Donald Brownlee, and its thoughtful counterpoint, the principle of mediocrity, a modern echo of the Copernican principle. The rare Earth hypothesis suggests that while simple microbial life might be relatively common, the emergence of complex animal-like life requires a remarkably precise and unlikely chain of events. Ward and Brownlee describe a series of filters. A planet must orbit within the habitable zone of a stable, long-lived star. It may need a large moon, like Earth's, to stabilize its axial tilt and keep climates from swinging wildly. It needs plate tectonics to regulate carbon dioxide and drive evolution, a magnetic field to shield it from stellar radiation, just the right amount of water, not too much, not too little, and the fortune to avoid sterilizing cosmic catastrophes like nearby gamma-ray bursts for billions of years. In this view, Earth might truly be a rare and precious oasis in the vastness of space. The principle of mediocrity offers a contrasting perspective. Given the sheer number of planets, those 40 billion potential Earths, and the universe's apparent fondness for complex chemistry, life may not be rare at all. Proponents, such as astronomer Caleb Scharf of Columbia University, point out how quickly life appeared on Earth as soon as conditions were suitable. Perhaps, they suggest, life is not some extraordinary fluke, but a natural, even inevitable outcome of chemistry and time. The debate between these ideas is far from resolved. It is a tension between the force of statistics and the weight of specific local evidence, a question that only continued exploration of our solar system through missions to Mars, Europa, and Enceladus, and the study of exoplanet atmospheres with JWST and future observatories can hope to answer. This quest for life is deeply entwined with our storytelling and imagination. The epic science fiction series, The Expanse, both the novels and the Amazon Prime adaptation, presents a compelling and realistic vision of humanity's future in the solar system. It imagines a time when humans have colonized Mars and the asteroid belt, but have yet to reach the stars. Then, with the discovery of a mysterious alien protomolecule, everything changes. The series is celebrated for its scientific realism, its faithful depiction of physics, orbital mechanics, and the physiological challenges of space. But its deepest resonance lies in its exploration of how humanity responds to the cosmic unknown. Perhaps the greatest challenge of discovering life beyond Earth is not technical, but philosophical, political, and even psychological. Are we truly ready for such a revelation? As we expand the horizons of knowledge, we are also developing the tools to one day leave our cradle entirely. Interstellar travel, once the province of imagination, is now a serious subject of study. One of the boldest endeavors is Breakthrough Starshot, a $100 million research program launched in 2016 by Yuri Milner and Stephen Hawking. Its audacious aim is to create a fleet of tiny, gram-scale star chips, each equipped with cameras, photon thrusters, and a delicate light sail. These probes could, in principle, be propelled by a massive ground-based laser to 20% of the speed of light, reaching the Alpha Centauri system, the nearest star system to our own, in just over 20 years. The engineering challenges are staggering. They include building a laser array with the power of 100 nuclear reactors, crafting sails only a few hundred atoms thick that can survive immense energy without vaporizing, and designing microelectronics capable of enduring decades of interstellar radiation. Yet, scientists and engineers from MIT, Harvard, and other institutions are steadily working through these problems. This is not a mission for tomorrow, but it is a beacon, a tangible project that says humanity's future need not be confined to a single solar system. It is a testament to the quiet power of long-term vision, and a reminder that patience, imagination, and perseverance are qualities we must nurture if we are to navigate the challenges of the centuries to come. Our journey through the chemical and biological potential of the galaxy brings us, at last, to a profoundly humbling thought. The Milky Way is roughly 13.6 billion years old, while our own solar system is a comparatively tender 4.6 billion years. If other technological civilizations have emerged somewhere among the stars, some of them might be millions of years ahead of us. What would their presence look like? Traditionally, the search for extraterrestrial intelligence, or SETI, has listened for radio signals. But a highly advanced civilization might leave subtler, yet far more extraordinary traces. Astronomers at the University of Rochester have speculated in papers published in the Astrophysical Journal about what such techno-signatures might be. City lights glimmering on the night side of an exoplanet, colossal orbital structures like Dyson spheres that dim a star's light and release it as waste heat in the infrared, or even chemical fingerprints of artificial pollutants such as CFCs, lingering in the atmosphere of a distant world. And yet, the cosmos remains silent. This profound quiet is what we call the Fermi paradox. But as our instruments become ever more refined, we are no longer simply listening for greetings. We are searching for the archaeological traces of engineering on a cosmic scale. In a sense, we are searching for our own potential, and in doing so, we are forced to look inward. What kind of future do we want for ourselves? Will we be a species that learns to steward its homeworld and reach for the stars, or one that succumbs to short-sightedness? The galaxy with its 40 billion possibilities, is quietly waiting for our answer. We have mapped the structure of the Milky Way, probed its mysterious heart, glimpsed its living chemistry, and imagined life among the stars. But to truly understand our galaxy, we must see it not as a static portrait, but as a living, breathing entity with memory. We must become cosmic archaeologists, reading the layers of stellar populations to uncover its violent, creative, and deeply intricate history. And we must examine our own role within this story, not merely as observers, but as participants whose choices are being etched quietly yet irreversibly into the geological and perhaps even cosmological record. Our exploration of the galaxy's past begins with its most ancient relics, the globular clusters. These are magnificent, dense spheres of hundreds of thousands of stars orbiting the galactic center like a swarm of ancient, flickering fireflies. They are the retirement homes of the Milky Way, filled with population 2 stars, incredibly poor in metals. The study of these clusters has been transformed by the Hubble Space Telescope and, more recently, the Gaia spacecraft. By carefully measuring the ages of their stars, combining their positions on the Hertzsprung-Russell diagram with their chemical composition, astronomers have determined that the oldest clusters, such as M92 and NGC 6397, are over 13 billion years old. They formed when the universe itself was still in its infancy, only a few 100 million years after the Big Bang. These clusters are not merely ancient, they are exquisite time capsules. They preserve the chemical fingerprint of the early Milky Way. A landmark study in 2018, published in Nature and using data from the European Southern Observatory's Very Large Telescope, examined stars in the cluster NGC 6752. The team discovered unique chemical correlations that could only be explained by the very first generation of stars, so-called population 3 stars. These primordial giants, perhaps hundreds of times the mass of our Sun, ended their brief, brilliant lives in catastrophic pair instability supernovae, dispersing their uniquely processed material into the surrounding gas. Through these clusters, we are granted our only direct window into that first violent chapter of cosmic star formation. But the history of our galaxy is far from a serene, unbroken tale. It is, in many ways, a story of cosmic cannibalism, written in the faint, ghostly streams of stars that weave themselves around the Milky Way. Thanks to the Gaia mission, which has measured the positions and motions of over 2 billion stars with exquisite precision, this story has shifted from speculation to something almost cinematic. We can now trace the remnants of past mergers not as static fossils, but as living, moving structures, stars still traveling together, their motions quietly revealing their shared, ancient origins. One of the most significant of these ancient collisions is the Gaia-Enceladus merger, also known as the Gaia sausage. Roughly 10 billion years ago, a sizable dwarf galaxy, perhaps a quarter the mass of the young Milky Way, collided with and was absorbed by our galaxy. Gaia has revealed the evidence in the motions of millions of stars moving along highly radial, sausage-shaped paths that plunge deep into the galactic center on elongated orbits. This dramatic encounter likely stirred the Milky Way's pre-existing thin disk, helping to form the puffy, thick disk we see today. It was a foundational event, one that reshaped the very architecture of our galaxy. More recently, we witness the ongoing dissolution of the Sagittarius dwarf spheroidal galaxy. Each 700 million year orbit, the Milky Way's tidal forces strip stars from this small companion, stretching them into a vast, faint river of light that circles our galaxy. A 2020 study in the Astrophysical Journal, using Gaia data, mapped this stream with exquisite precision, uncovering subtle kinks and folds, gravitational scars from past close encounters. Through this, astronomers can probe not just the stream itself, but the dark matter halo that guides its path. It is astronomy as forensic art, reading the galaxy's history in its most delicate structures. This story of a galaxy built through mergers is beautifully illustrated in the Netflix series Our Universe, narrated by Morgan Freeman. In the episode The Cosmic Clock, the Milky Way's formation is shown not as a gentle gathering, but as a series of violent collisions, with dwarf galaxies torn apart and woven into the growing spiral. Freeman's voice intones with quiet gravitas. We are all, quite literally, stardust, but we are also the children of cosmic violence, our very existence dependent on the ancient shattering of other worlds. What once seemed poetic is now grounded in hard data, giving us a visceral sense of our galaxy's turbulent youth. As we look to the Milky Way's past, we are also confronted with a sobering chapter of its present, the Anthropocene. This proposed geological epoch marks a period in which human activity dominates the climate and ecosystems of Earth. The Intergovernmental Panel on Climate Change, in its 6th assessment report, synthesized over 14,000 scientific papers to state clearly, human influence has warmed the planet at a rate unprecedented in at least the past 2 millennia. Atmospheric CO2 levels are now higher than at any time in the last 2 million years. Satellites from NASA, NOAA, and ESA are keeping watch over these changes from space. NASA's GRACE missions have precisely measured the rapid loss of ice from Greenland and Antarctica, contributing to rising seas. Meanwhile, the Orbiting Carbon Observatory too maps the sources and sinks of carbon dioxide across the globe, revealing how nature's gentle balance is being overwhelmed by industrial emissions. This is not merely a local concern, it is a transformation on a planetary scale. A 2022 WWF report noted that global wildlife populations have declined by an average of 69% since 1970. A stark reminder of the fragility of the biosphere that took billions of years to evolve. This change we've brought upon our world sits within a much wider, almost cosmic story. You might think of that famous pale blue dot photograph captured by Voyager 1 back in 1990, when the spacecraft was already drifting beyond Neptune. In that picture, our entire home appears as nothing more than a tiny, shimmering speck. Carl Sagan's words about it echo even more deeply today. Look again at that dot. That's here. That's home. That's us. A gentle reminder that everyone we've ever known, everyone we've ever loved, every moment of our shared human journey unfolded on this little mote of dust suspended in a sunbeam. And so, this planet, the only one we know to cradle life, is precious beyond measure. The climate crisis isn't simply a matter of economics or politics. It's really a test of our species' ability to care for the world that shaped us. In many ways, it may well be the most important project we've ever taken on, a quiet responsibility to protect the delicate, conscious stardust that the Milky Way has so far managed to gather into life here. that responsibility doesn't end at the ground beneath our feet. It reaches into the space above us too. The rush to place ever-growing constellations of satellites into orbit, from ventures like Starlink and Project Kuiper, has introduced a new kind of threat: the gradual dimming of the natural night sky. Astronomers from groups such as the IAU and NOIRLAB have voiced their concern, publishing studies showing how these thousands of satellites leave bright trails across telescope images and add interference to once quiet radio bands. The star-filled sky that guided, inspired, and comforted humanity for countless generations is beginning to fade beneath a veil of artificial light. And there's a gentle, bittersweet irony in that. In reaching for greater connection with one another, we risk losing our view of the very cosmos that gave us our first sense of wonder, the place where our story began. Yet within all these challenges, there rests an even grander and rather hopeful vision for humanity's future. The idea of shaping worlds on a planetary scale, something we often call terraforming. For now, it lingers mostly in the realm of science fiction, but it's also a topic that scientists discuss quite seriously. Mars, in particular, tends to capture our imagination. In the series The Expanse, shown on Amazon Prime, we're treated to a vision of a fully transformed Mars, complete with a breathable atmosphere and flowing water, the result of centuries of quiet determination. In reality, as explored by researchers from places like the University of Colorado Boulder and in NASA's own concept studies, the truth is far more intricate. To remake Mars into a second Earth, we would need to overcome 3 enormous hurdles: thickening its thin atmosphere, warming the frozen planet, and eventually making that atmosphere safe to breathe. Ideas have included placing giant mirrors in orbit to shine sunlight onto the ice caps, releasing potent greenhouse gases produced on the surface, or even steering ammonia-rich comets into the planet to add essential nitrogen. But a significant study published in Nature Astronomy in 2018 offered a rather sobering pause. It found that Mars simply doesn't hold enough accessible carbon dioxide to build a thick, protective atmosphere. Even if we released every last bit of CO2 locked in the polar ice and the soil, the pressure at the surface would only reach about 7% of Earth's level, far too low for liquid water to persist, and still requiring humans to wear pressure suits outdoors. So while the dream of creating enclosed, sheltered habitats remains very much alive, a full planet-wide transformation may always sit just beyond our scientific reach. It doesn't extinguish the hope of becoming a multi-planet species, but it does gently ground that hope in the firm laws of physics. At the far edge of imagination lies something even more breathtaking: the idea of a Dyson sphere, a colossal megastructure built to surround an entire star and gather all of its energy. First proposed by physicist Freeman Dyson in 1960, it's considered the hallmark of a highly advanced Kardashev Type II civilization. Building a solid shell is beyond what physics will allow, but a Dyson swarm, countless solar collecting satellites orbiting in harmony, is at least theoretically possible. Researchers at Oxford's Future of Humanity Institute have explored the idea, noting that the true limitation isn't energy but raw material, to the point where you'd need to dismantle a whole planet simply to gather enough resources. Searching for such structures has become a fascinating part of modern SETI work. Astronomers have sifted through infrared data from NASA's WISE mission, looking for stars that appear oddly dim in visible light, yet bright in the infrared, a potential sign of a star wrapped in a cloak of energy-collecting machines. A few intriguing stars, such as the famously puzzling Tabby's star, have been identified, though the explanations so far point to natural causes like drifting dust or comets. Still, the search continues, quiet, patient, and hopeful. It reflects something quite touching about our species, this gentle desire not only to survive on a single world, but to one day care for and explore an entire star system, guided by curiosity, imagination, and the soft glow of distant suns. This long-term view really does matter. The Milky Way itself has a future stretching out for tens of billions of years, an almost unimaginable span of time. Our sun, sitting comfortably in its middle age, still has around 5 billion years of fuel left. After that, it will slowly begin to swell into a red giant, its outer layers drifting outward and likely enveloping Mercury, Venus, and perhaps even Earth, before it settles down again as a small, dense white dwarf. Far beyond that, the slow dance between our galaxy and Andromeda will reshape the very structure of the night sky. And on timescales, even grander still, the quiet push of dark energy will continue to accelerate the expansion of the universe, gently pulling everything farther and farther apart until our local group of galaxies becomes an isolated island adrift in the vastness. It's a perspective that can feel immense, yet strangely comforting, a reminder that we are part of a story far older and far longer than ourselves. Our human story is, in truth, just a single, brilliant flash against an immense and ancient darkness. And yet, within that fleeting moment, we have opened our eyes to the cosmos. We've unraveled the life cycles of stars, traced the ancestral threads of our galaxy, and sent our quiet, robotic explorers all the way to the edge of the solar system. The choices we make now, to care for our fragile biosphere, to handle our growing technological power with wisdom, to approach the unknown with curiosity rather than conquest. These choices will shape whether our brief spark fades quickly or becomes the kindling for a flame that might, in its own small way, glow through the galactic night for ages to come. The Milky Way has given us everything, and now, softly, the question hangs in the air. What will we give back? We've traveled so far together, across space and time, from the shimmering quantum flicker near a black hole's horizon to the slow, majestic dance of galaxies colliding. We've become mapmakers of dark matter, patient detectives of ancient stellar streams. But now we arrive at the most delicate part of our voyage, the inward journey into consciousness, meaning, and the quiet, haunting question of whether we are truly alone. Here, we begin to consider the Milky Way not just as a physical structure, but as something with philosophical weight, an existential backdrop. What does it mean to be a thinking being in a vast, indifferent cosmos? And what responsibilities arise from that rare, flickering consciousness? This inward path begins with the tools that let us see the galaxy at all, our senses and the minds that interpret them. For most of human history, the Milky Way was a place of myth and wonder. The ancient Greeks imagined it as a spray of milk from the goddess Hera's breast. The Kung people of the Kalahari pictured it as the glowing embers of a great distant campfire. These stories weren't wrong. They were human. They were our early attempts to weave meaning into that luminous river of light above. Then came the scientific revolution. When Galileo lifted a simple telescope to the sky and saw the Milky Way resolve into uncountable stars, the mystery didn't vanish. It simply transformed, offering us a new kind of wonder, the wonder of understanding. And that understanding has always been a deeply human drama, full of debate, determination, and remarkable insight. Think of the famous Great Debate of 1920 between Harlow Shapley and Heber Curtis. Shapley, drawing on his work with globular clusters, argued passionately that the Milky Way was the entire universe and that the spiral nebulae were just clouds within it. He was wrong, of course, but he was reasoning from the best evidence available at the time. Curtis argued the opposite, that those spirals were in fact whole other galaxies, island universes of their own. The debate didn't settle the question, but it framed the cosmic mystery of the age. And just a few years later, Edwin Hubble resolved it by measuring Cepheid variable stars in Andromeda, revealing its true distance far beyond our own galaxy. Historians and writers, like Timothy Ferris in The Red Limit, often return to this story because it shows how science, at its heart, is self-correcting, driven by people who may be brilliantly, even famously wrong on the way to uncovering the truth. Our instruments of discovery have grown from Galileo's modest little spyglass to the breathtaking marvels we send into space today. The James Webb Space Telescope, a collaboration between NASA, the European Space Agency, and the Canadian Space Agency, is a perfect example. Its creation was a long, intricate saga of international teamwork and extraordinary engineering. Watching its vast, gold-plated mirror unfold in the cold silence a million miles from Earth was one of the boldest technological moments in history. And every image it sends back, from deep-field glimpses of galaxies being born to the delicate spectra of distant exoplanet atmospheres, is more than mere data. Each one is a quiet postcard from the frontier of our understanding, a reminder that we are a species who refuse to stop at the edge of the sky. This unending curiosity, this quiet, insistent desire to know what lies just beyond the next horizon, is explored with remarkable tenderness in the Apple TV Plus series For All Mankind. Though it paints an alternate history, its emotional truth rings very real. The show captures the inner drive of astronauts, engineers, and mission planners, that almost biological need to see what's over the next hill. It mirrors the genuine spirit that flows through places like NASA, ESA, and even private ventures such as SpaceX. At its heart, the series asks a profound question. Is exploration simply a luxury, or is it something woven into the very fabric of an intelligent species? The fictional astronaut Ed Baldwin gives voice to the same sentiments expressed by real pioneers like Chris Hadfield and Samantha Cristoforetti, when he declares, "We're not here to be safe, we're here to see what's next." It's a striking thought that our curiosity often pushes against the harsh realities of space itself. Those realities were documented in extraordinary detail through NASA's twin study, published in Science, which followed the physical and genetic changes experienced by astronaut Scott Kelly during his year in orbit, compared to his twin brother Mark, who remained on Earth. It was a reminder of just how demanding space is on the human body, and how far we are willing to go in the name of discovery. And yet, the further we venture outward, the more we are confronted by a strange and quiet puzzle, the Fermi paradox, the overwhelming silence of the cosmos. With billions of potentially habitable worlds in our galaxy alone, why is there no sign of anyone else? No signals, no artifacts, no whisper of a neighbor. The possible answers form a spectrum that stretches from the gently hopeful to the deeply unsettling. In a 2018 paper for Acta Astronautica, astronomer Adam Frank and astrophysicist Woody Sullivan explored these possibilities with careful, thoughtful detail. At one end of the spectrum lies the rare Earth hypothesis, the idea that the delicate series of events leading to complex technological life might be extraordinarily uncommon. At the other lies a far more troubling notion, the Great Filter, first formalized by economist Robin Hanson. It suggests that somewhere along the long journey from simple chemistry to a civilization capable of crossing the stars, there is a near insurmountable barrier. And the unsettling possibility is that this barrier may not be behind us, but ahead. It could be that once civilization gains the power to reshape its environment, the risk of self-destruction rises sharply. Nuclear conflict, engineered pandemics, or even the sort of climate instability we are now creating might be examples of such filters. In this light, reports from the IPCC and wildlife assessments like the WWF's Living Planet report take on an almost cosmic weight. They become something more than environmental updates. They become quiet evaluations of whether we can navigate our own technological adolescence. Other ideas, while gentler, are no less thought-provoking. The zoo hypothesis suggests that advanced civilizations might already be aware of us, choosing to watch from afar until we reach a certain level of maturity. The estivation hypothesis imagines ancient intelligences lying dormant, simply waiting for the universe to cool so that computation becomes more efficient. These theories may not be testable in any traditional sense, but they act as mirrors, reflecting our own hopes, fears, and imaginings about what it means to be intelligent in a vast and silent cosmos. They remind us that the search for others is, in many ways, a search for ourselves, for meaning, for connection, and for our place in the quiet, starlit expanse. This search for meaning in a universe that so often feels silent and indifferent is something modern cinema has explored with remarkable sensitivity. Denis Villeneuve's Arrival is perhaps one of the finest examples. It isn't a story of laser battles or looming invasions, but a meditation on communication, on linguistics, and on the mysterious nature of time itself. In the film, linguist Louise Banks, played with such quiet depth by Amy Adams, begins learning the circular, non-linear language of the heptapods. And as she does, her perception shifts. Time no longer unfolds like a straight path. Instead, it appears as a complete whole, all moments woven together. The film suggests that our consciousness, our very experience of reality, is shaped by the language we use to interpret it. The weapon is the language, one character warns, though in truth, it is less a weapon than a doorway to an entirely new way of seeing. This idea has a real scientific echo in the Sapir-Whorf hypothesis, which proposes that the structure of a language influences the thoughts and perceptions of its speakers. It gently nudges us toward a profound question. If an alien species evolved in a completely different environment, shaped by different senses, different constraints, different needs, would their consciousness be anything like ours? Would their experience of the Milky Way, their sky, their universe, their very notion of existence be recognizable to us at all? It may be that the true challenge of first contact isn't technology or distance or even biology. It might be learning to understand a mind shaped by a reality we have never imagined. This brings us to perhaps the most intimate connection of all, the cosmic story written within our very bodies. Astrobiology, once a speculative field, now sits firmly at the crossroads of biochemistry and genetics. The discovery of extremophiles here on Earth, creatures thriving in boiling vents on the ocean floor, in radioactive waste, or hidden deep within the dry soils of the Atacama Desert, has widened our sense of what habitable really means. These hardy organisms, studied by institutes such as the Marine Biological Laboratory in Woods Hole and NASA's Astrobiology Institute, are glimpses of the sort of life that might dwell in the hidden oceans of Europa or the methane lakes of Titan. Tardigrades, those tiny water bears, tell a particularly astonishing story of resilience. These microscopic beings can survive the vacuum of space, intense radiation, and temperatures close to absolute zero. When an Israeli spacecraft carrying tardigrades crashed into the moon in 2019, they almost certainly did not survive. Yet the incident sparked an important ethical conversation about planetary protection. International guidelines, shaped by COSPAR under the United Nations, exist precisely to prevent such accidental contamination. If we can unintentionally send Earth life elsewhere, we must wonder, could life once have arrived here the same way? The panspermia hypothesis remains speculative, but not impossible, supported in part by experiments from the exterior of the International Space Station, showing that certain microbes can endure the harshness of space for surprising lengths of time. And so, standing at this crossroads, one path leading inward to our own fragile planet, the other stretching outward toward the stars, we face a choice about the story we wish to tell. One version speaks of separation and conquest, treating the universe as something to extract from. The other, far richer and more humane, is a story of connection and stewardship. It's a narrative Stephen Hawking championed throughout his life. In brief answers to the big questions, he urged us gently, remember to look up at the stars and not down at your feet. Be curious. It matters that you don't just give up. His words linger like a quiet lantern in the dark. This, all of this, is the legacy of the Milky Way to us. It is not merely the place we inhabit, but the teacher that formed us. Its laws shaped the atoms of our bodies. Its history offered the stability life needed to flourish. Its vast, contemplative silence has stirred our deepest questions and ignited our highest aspirations. To understand the galaxy is, in a very real way, to understand ourselves. And in caring for our delicate little world, we honor the immense and beautiful cosmos that gave us birth. We become, in a small but meaningful way, the universe's way of caring for itself. And now, we find ourselves at the end of our great voyage, and curiously, at its beginning. We have drifted through the quiet gravitational sea of the dark matter halo, watched the radiant, sometimes violent lives of stars along the spiral arms, and stood in awe beneath the influence of the galactic core. We've risen above the plane of the Milky Way to witness the slow, stately motion of neighboring galaxies. We've explored the chemistry that seeds life, confronted the cosmos' profound silence, and reflected on the remarkable weight of consciousness in a seemingly indifferent universe. Now, all that remains is to gather these threads, to weave them into a final vision of our home, our future, and our place within this vast and ancient galaxy. Let's begin gently by returning to our cosmic address, now seen with the clarity only such a journey can provide. We aren't simply on a planet circling an ordinary star. We live on a small, water-rich world orbiting a stable, middle-aged G-type star, just one among hundreds of billions in the Milky Way. Our solar system rests inside the Orion Spur, a quiet bridge between the grander Sagittarius and Perseus arms, about 26,000 light-years from the galactic center. This position is no accident. Researchers writing in astrobiology have refined the idea of a galactic habitable zone, a region far enough from the tumultuous core to avoid destructive radiation and gravitational chaos, yet close enough to benefit from the heavy elements forged in ancient supernovae. Our quiet corner of the galaxy, this gentle cosmic suburb, has offered 4.5 billion years of relative tranquility, enough time for biology to blossom into consciousness. It is a delicate stroke of cosmic fortune, and our story unfolds within it. This precise corner of the galaxy where we find ourselves is not fixed, but wonderfully dynamic. We are always in motion, carried along by the great celestial currents. Our sun, and with it, everything we know, sweeps around the galactic center at about 230 kilometers per second, completing a single galactic year, only once every 225 to 250 million years. At the same time, we gently rise and fall through the thin plane of the Milky Way's disk, a slow oscillation that may have nudged Earth's climate over deep time. And thanks to the remarkable data from the Gaia spacecraft, we now know that our local neighborhood is still trembling with the faint echoes of ancient galactic encounters. A 2021 study in Nature Astronomy revealed that our solar system is still being ever so slightly tugged by the remnants of the Sagittarius dwarf galaxy as it's gradually torn apart. It's a quiet reminder that we are not simply passengers in the Milky Way, but participants in its vast gravitational story. This broad, interconnected view of our place in the galaxy is one of the triumphs of modern astronomy, and very soon, NASA's Nancy Grace Roman Space Telescope will expand this perspective dramatically. Set for launch in 2027, the Roman telescope will carry out a wide-field survey far greater in scale than even Gaia's extraordinary census. It will detect thousands of distant planets using microlensing, including lonely rogue worlds drifting freely through the darkness. It will also help trace the hidden architecture of dark matter within the Milky Way, measuring the subtle distortions that gravity imprints on the light of faraway galaxies. Roman will give us more than a map. It will offer a blueprint of our galaxy's structure, both visible and invisible. Our growing curiosity about dark matter and dark energy is shaping the future of physics itself. Deep underground, the LZ and XENONNT experiments continue their patient search for dark matter particles. Meanwhile, the Cherenkov Telescope Array, the next great observatory for gamma-ray astronomy, will look to the skies for the faint signatures that might appear if dark matter particles collide and annihilate one another. In orbit, ESA's Euclid mission, launched in 2023, and the forthcoming Roman telescope will create the most intricate 3D maps of the universe ever made, tracing how dark energy has shaped cosmic history. The results, analyzed by teams at MIT, Caltech, and the University of Edinburgh, may finally tell us whether dark energy is truly constant or something more subtle and surprising? The fate of the cosmos, its slow fading into darkness, or some entirely different destiny, rests on this question. And yet, even as we contemplate the physics of the universe, we find ourselves brought gently back to the human scale. One of the most touching moments in Apple TV Plus's For All Mankind is not of rockets or vast Martian vistas, but of a small, steady garden glowing inside a habitat on Mars, with Earth shimmering as a tiny blue star in the pink sky above. It's a quiet, hopeful vision, not simply reaching other worlds, but helping life take root there. This too echoes the spirit of NASA's Artemis program, a shift from brief visits to a sustained presence. The technologies being developed now, from extracting water from lunar ice to 3D printing habitats from the moon's dusty regolith, are the first careful steps toward making that fictional Martian garden something real. Much of this work lives not in glossy announcements, but in rigorous technical papers and the steady scholarship of journals like New Space. But for all our ambition, we must still face the limits of our own biology. The NASA twin study, published in Science, gave us our first detailed look at how profoundly spaceflight touches the human body. Scott Kelly's year in orbit altered his gene expression, his cognitive performance, even the delicate ecosystem of microbes in his gut. Most of these changes eased once he returned home, but some, including subtle chromosomal shifts and lingering cognitive effects, remained. A journey to Mars, lasting perhaps 3 years, will expose future astronauts to levels of radiation and microgravity unlike anything experienced before. Researchers are preparing safeguards, concepts for spacecraft with artificial gravity, new medicines to protect the body from radiation. But the challenge is immense. It may prove to be one of the great biological filters humanity must learn to cross. Through all of this, a quiet truth emerges, that our quest to understand the cosmos always brings us back to ourselves, our fragility, our resilience, our curiosity. These are as much a part of the story as galaxies and dark matter. And as we look ahead to the worlds we may one day call home, we are reminded that the universe isn't something distant and indifferent. It is the very place that shaped us, and the place we continue, gently and bravely, to explore. And what if we truly succeed? What lies at the far horizon of this great outward journey? For thinkers like the late Stephen Hawking and philosophers such as Nick Bostrom of Oxford's Future of Humanity Institute, the answer is grounded in something very simple: survival. Keeping all of our hopes, our history, and our biology confined to a single planet is, over long enough timescales, a fragile arrangement. A self-sustaining settlement on Mars would be a kind of cosmic insurance policy, a safeguard against the unpredictable. But the vision stretches further still. Projects like Breakthrough Starshot, ambitious as they are, mark a quiet turning point in our imagination. They shift us from the idea of merely escaping our planet to the far more inspiring notion of exploring our stellar neighborhood with intent. Even if only part of its technology, the powerful laser arrays, the delicate light sails, the resilient miniature electronics, ever becomes practical, it would reshape space exploration entirely. Journeys to the outer planets could shrink from years to weeks. The resources of the asteroid belt could become accessible. The solar system itself would begin to open. Holding this long view also helps us understand the urgency of the challenges we face here at home. The IPCC's 2023 synthesis report is the starkest warning yet. It tells us, with clarity and without drama, that to avoid the most severe warming, global greenhouse gas emissions must fall by nearly half by 2030, an astonishingly short time. This is not a distant concern. It is unfolding now. The report describes a world already slipping into more frequent heat waves, deeper floods, harsher droughts, and rising seas that will displace millions and strain food systems across the globe. The WWF's Living Planet Report 2022 adds another layer, revealing a 2/3 average decline in monitored vertebrate wildlife populations since 1970. We are destabilizing not only the climate, but the living fabric of the world that sustains us. Meeting this crisis is the defining task of our time. It is the groundwork required for any future that reaches beyond Earth. The technologies we need, advanced nuclear energy, next-generation renewables, carbon capture, resilient grids, sustainable farming, are the very same tools that would allow a thriving civilization to flourish here and eventually take its place among the stars. The UN's Sustainable Development Goals are more than a humanitarian checklist. They are a guide to passing through our own technological bottleneck, to building a stable, just, and inventive planetary society, capable of reaching outward with wisdom rather than desperation. And as we gaze ahead, it's equally important to look inward to the meaning and the mystery wrapped within everything we've learned. The Milky Way has given us a universe filled with breathtaking beauty and quiet brutality in equal measure. It offers the gentle glow of starlight and the violent brilliance of supernovae, the chemistry that makes life possible, and the cold silence of the cosmic void. We are shaped by all of it, the creative forces and the destructive ones, the serene and the chaotic. In a very real way, the galaxy has made us what we are. And so, the final, lingering question remains: are we alone? The silence that surrounds us is deep and unwavering. Yet within that silence, there is something that feels very much like a summons. If, by some extraordinary twist of fate, we are the only, or perhaps the very first, intelligence to emerge in this corner of the galaxy, then a remarkable responsibility falls to us. We become the caretakers of meaning itself. In that sense, we are the custodians of the universe, the ones who give voice to the Milky Way's unfolding story. Everything we create, our art, our science, our music, our myths and memories, becomes a way for the galaxy to understand its own beauty through us. The plays of Shakespeare, the quiet brilliance of Einstein's equations, the soaring symphonies of Beethoven, even the intricate code that shapes our digital lives. All of it becomes part of a much larger record, as intrinsic to the cosmos as the faint afterglow of the Big Bang. In the stillness of the universe, we are the ones who speak. Our journey comes full circle, returning to where it all begins, with wonder. The pale, shimmering arc of the Milky Way stretching across the night sky is both a bridge to our distant past and a guide to our cosmic future. It reminds us of where we came from and hints at what we might yet become. We are fleeting, delicate creatures on a small, fragile world, and yet, in the same breath, we are the eyes and the mind of the cosmos. We have peered into the heart of our galaxy and begun to grasp its story, and in doing so, we have discovered something more precious than a final answer, a purpose: to cherish and protect the fragile spark of life we have been given, to search for other sparks in the darkness, and to ensure that, For one brief and shining moment, the story of this spiral galaxy includes a chapter written in curiosity, consciousness, and hope. The galaxy is immense, the galaxy is ancient, and the galaxy is home. Sleep now and let your dreams wander among its billion suns, for you are a child of this magnificent cosmos, and in your dreaming, the galaxy dreams with you.